Cool. Okay, so in the afternoon part of the session, we're going to go into compute shaders and basically learn how they can be used to do physics calculations, which in this example means building a particle system from scratch, which is sort of like a very, it's like the hello world of, of like doing physics on the GPU, I would say. So we're going to try to start from there and get as far as we can and learn how to basically like do that, and then use the particles to drive visual effects as well. Hopefully we'll get there, but all this is done. Can show you just real quickly the complete system that we'll be trying to get to, which is gonna run. Let's see. Which is not running. Oh, hello. It's the wrong project. There we go. Yeah, cool. So it's kind of like. No, sorry, I'm just showing this as a kind of like, here's where we're going to get to, and we're going to start completely from scratch, so no need to get excited. We have a long way to go. So does everybody sort of have a general idea for what a compute shader is, or is that something?
No.
Perfect, all right. Great, excellent. So a compute shader is essentially a program that runs on the GPU the same way that a vertex or a fragment shader runs. The difference is that it is not tied into any of the other parts of the graphics card that are meant for rendering. So nothing gets put on a screen, nothing gets, there's no like real notion of geometry. That's all stuff that is reserved for the other pipelines, like the fragment, vertex, geometry shaders, all that stuff. Compute shaders are specifically designed for doing mathematical operations, basically in a general sense. So we're not really going to think too much about lighting in this sense. We're really just going to be doing math and doing it really, really fast. So the first demonstration I have in this introduction scene is one to take a look at. So this is more or less just the most basic way to fill a texture, which is essentially what we were doing with fragment shaders before. All those different math functions, we're just filling the texture. And it's gonna all run very slow today, which is awesome. What's that? It probably is, right? Yeah, all right. Maxing out both GPUs. If that gets to be too bad, I'll stop recording. I just try to have this for posterity. Okay. So if we play this, wow, yeah, this might not work at all. See this simple ramp. So this is basically what we were doing before. Just basically have the UV become the red channel of this texture. But in this case, we're using a compute shader to do that. So this is a little small. I'm just going to go through each line kind of because it's so short and sort of describe what each one does. So the pragma kernel, a kernel is basically a piece of code that runs on the GPU. It's like a function, but a chunk of code, and it runs sort of in an arbitrary way that you have to define. This just defines a kernel called CS_main. CS_main is down here. And the next line describes a read-write render texture, 2D, meaning a two-dimensional texture that is like a render texture in C#. Everyone know what a render texture is? Yeah, no, anyone? Okay, cool. Render texture is basically just a texture that you can use to render to, and then it gets saved on the GPU, and you can reference it other places. So it's basically you create it on the CPU, but it lives on the GPU, and you can write to it. So I'll go through how that got created. And then we have a few of these variables, parameters, which is just like what we saw in the other shaders. In this one, you do have to define time yourself, but it still gets set by Unity. It just is not declared unless you declare it. And because this sort of like doesn't know anything about the geometry it's operating on, we have to calculate these UVs based on the index. So I'll back up a little bit and sort of like talk about how these IDs get defined and how a shader executes. I'm going to go to the whiteboard. Is it okay if I erase this? Yeah, maybe. Okay. So, render texture. Made up of pixels, right? Like in here, here. Textures are made up of pixels in X, Y direction, yeah? This is all just a primer. We're going to go over all this stuff a few times. But for this example, we're drawing this circle. We have basically pixels that are defined in X, Y direction. When we dispatch a shader, that's what it's called. When we execute code, we're going to tell it basically how many times to execute in this direction, how many times to execute in this direction, and all those are going to splat like the paintball demo earlier, happen all at once, and that code, that little piece of kernel code, is going to run for each of these, essentially. Does that make sense? Keeping you so far? Cool. In the shader, this CSMin, this ID, refers to basically where in the X direction and where in the Y direction we are in that paintball gun, essentially. So we have X that goes from here, from 0 to, the width. And we have Y that goes here, 0 to the height. So since we want to use UVs, we have to know the resolution out here and the height and width. So we basically just take the ID dot XY, divide it by the resolution of the texture, and that gives us a smooth value between 0 and 1, and 0 and 1 like that. Make sense? So then we can use all these really kind of like clever functions that we've learned about in the last section to draw into our texture. So why would you want to do that? I have another, and similarly to, there's what we saw before, you can add time. Oh, what did I do? Oh. Something like that, but it needs to be a sign or something, or frac. Can use the same kind of thing to like create these animated textures to use elsewhere. Frac, so that's the fractional part. So basically as time increases, it's going to keep going up way beyond 1. just takes the like the decimal part of it, basically. It's not important so far, really. This is mostly for demonstration, like I said. Why you'd want to use this. I have this other script called render cubes. If you add it here and select cube for cube mesh and cube grid for material, they're all in here. And hit play. This is basically, this material is using the red channel of the texture to define the height of the cubes. Oh yeah, how do I do that? Do I need to change my resolution? Wow, is Unity going to respect that? That's the real question. Might have to kill OBS. Is that any better? Do I need to go bigger? It looks the same. I think it's bigger, but I can go bigger. Yeah? A little more? Okay, yeah? Great. Okay, cool. Thank you. So, I'm not going to really go too deep into this because it's not super relevant to building a particle system, but I just wanted to sort of show you how, you know, using these textures, you can sort of like drive different parameters of geometry as well, and I mean, yeah.
I have like a main screen, I still have like a red one rendering. I only can see cubes in the screen.
What's that? Did you add the render cube script?
Yeah, I mean, I can see the cubes in the scene, but in the game view, I only see texture. It's like colored still.
Oh yeah, so there's this debug size. Does that help you? That should change sort of the size. Yeah, okay, cool. So basically I'm just drawing that texture directly to the screen. You can unclick it, click it on off. I will go quickly through the cubes, render cubes script.
So when you're dealing with like a million particles in the future, is going through a texture mostly a way of having like a good way to debug it, or is it all, are there other things that are useful? And is there anything, is it a bottleneck at all performance wise to go?
The thing that I would use the texture for with a particle system would be something like if I wanted to define parameters of the system via screen space. So I have an example in another project I could show. This might be a little off the beaten path for for this particular thing. So I think we'll just move on and start talking particles.
Shader description for a second again?
Yeah, so for the compute shader. Yeah. So this was mainly just to demonstrate how you can also use compute shaders to fill textures and use those sort of in other parts of your program. But
yeah, I was going to say, compared to, let's say, filling up a texture on the CPU, where you iterate through every pixel and like set it, it can be pretty fast, but this is way faster. It's just like everything's happening on the GPU, and you don't ever have to like, there's no bottleneck
like a fragment shader.
Yeah.
I think this could potentially be faster than a fragment shader because it doesn't go through any of the other pipelines.
Oh, right, because it's not doing every fragment, so it probably can even like
Yeah.
just do a points that it's encapsulating potentially.
Yeah.
Update the object it doesn't see, I guess.
Yeah, something like that, and it's also not tied to like the render thread as much. So
Maybe come back to the cubes after doing the basic.
let me come back to the cubes. Okay.
Is this drawn on the origin on this GUI?
Yeah, so it's just a GUI command. Okay. We'll move on to this, and I'm going to go a little back to the whiteboard and sort of talk through what a particle system has and what parts of that live where. What's sort of, yeah?
If you want to explain this brief, you don't explain random cubes too.
I can.
Exactly, very simple.
Yeah, I can do that a little bit. It's actually going to be really similar to how we build the system itself.
And we can come back to it later.
I can come back.
I think it makes more sense after we go through.
Yeah, I think it might make more sense after that. Cool. So everyone probably has some idea of like what a particle system is, right? I think when everyone raised their hand, pretty much when they said has like anybody touched one, right? Has anyone built one from scratch in any way?
Yeah, but not like any sort of advanced scripts.
Cool. Like CPU, like move stuff around.
Yeah, I did block in CPU, but just
Block.
objects and like graphics shaders.
Nice, yeah, that's cool.
But not
We won't quite get into like flocking and stuff where particle interaction like that, because that definitely complicates things on the GPU. If that kind of stuff is really interesting to you, you can talk to me after and we can maybe like talk through how you do that. But we'll save that kind of for the end. I think I left a little time for just like those sorts of topics. Basically what we're going to focus on is as many points as we can moving in as many directions as we can, but they won't be bouncing off of each other, they won't be interacting with each other, but they will be interacting with outside forces. And you can create some like really nice visual effects, and I've used it a ton in my work in VR and in other types of projection, interactive experiences and stuff like that. People really love playing with particles in VR especially. If you've never tried David's project, Cosmic Sugar, highly recommend it.
Let's install it over here if anybody wants to try it later.
It's just like this awesome particle sandbox in VR. So stuff like that really got me interested in it, and I have like a background in math and like doing a lot of physics, and it just sort of like made sense to go that way, and like that's sort of how I helped like learn graphics in the first place and why. It's really fun, in my opinion. So let's talk about like what the particle is a little bit. Basically, a particle is a point, right? It's a piece of dust. That piece of dust can be represented as an object, as a cube. In most cases, we're seeing it as points, maybe like some stars, something like that, if you want to stylize it. But more or less, we're looking at a point. Usually those points move, so some kind of velocity. I'm actually going to call that position. So like a position and a velocity is sort of like the most basic thing, right? Then you move it, you calculate your velocity, you update it, move on. Great. So simple enough. How do we do that with compute shaders? So at the heart of everything, we'll have basically a shader. This is basically our compute update. compute shader. We have our, normal sort of like Unity script. So we're going to have like a setup and an update, right? That is probably pretty familiar. And then we'll have some way to basically render it, which is like a render shader. Cool. So that's, the three parts that are crucial. So we have to have a way basically to store these positions and velocities. So they're called slightly different things, whether you're in the shader language or the scripting language. Here, they're called a compute buffer. And here they're called a structured buffer. Both those are types, like how you define a variable as you would in scripting. No real difference. This is just a reference to this that lives on the CPU, so you can do operations on it. So this is basically where we're going to store our particles. A buffer is just a block of data. So the interesting thing about these is you sort of have to define that for yourself. With traditional texture, that's also a buffer, but it's sort of it's made for float fours, more or less, like it's colors, right? So it's a color buffer, it is a texture. Two-dimensional color buffer is a texture. In this case, we're mostly going to be using single-dimensional buffers, like an array. And we'll define that structure, which we'll get into a little bit later. So this is basically going to be just like a long array. And these guys are going to live in here, right? So the same way if you were going to, hold everything in a list or an array, you can do that in a buffer on the GPU. So that's going to be sort of like where all these particles live. When we do it the first time, we're going to basically like fill this buffer in setup. And we're going to update, oh sorry, it says update buffer. Sorry, we won't actually update the buffer there, we'll call the shader to update. And this will have our, kernel, the ID, and do the stuff on the particle system, basically. Then this same structured buffer will be shared with the render shader as well. And this is going to basically do our, we'll have vert and frag in there, as we saw before. It's just instead of having it on geometry, it's going to be on geometry that we render with a different command I'll show you. And we'll be setting the position of all those vertices based on this position here. That all sort of make sense?
Does the compute buffer contain like all of the kernels?
No.
Whereas the structured buffer is like each individual one? Or?
So this also has, the Unity script will also have something called a compute shader. So compute shader is a reference to all the kernels and everything, which would actually be, how you execute code on the GPU. The compute buffer is just this data. So you can have multiple compute buffers. You can have textures. it's just a way to like store data in an arbitrary way. So when I say compute buffer here, the Unity has no idea what is in that buffer. It just knows it has this much available on the GPU essentially. And when you create it, as we'll see, you'll tell it that based on like how you want to structure your data. Yeah.
Can you explain what kernel is?
Sure. So kernel is basically just a. Let me pull up the code. Like this is a kernel. So this function, similarly to like a vertex or a fragment program, it'll get executed for every, like those get executed for every vertex or fragment. This will get executed based on basically dimension of, so you can tell it how many times to execute more or less. And you have to know how many times to execute it. We'll go through how that works.
And you can have like 1,000 pixels resolution, so you have like 1,000 kernels.
No, you have the one kernel, and this gets executed 1,000 times.
And you have multiple kernels.
You can, yeah.
Why? Like, why would you use multiple kernels?
I'll show that in the second section because we'll use one kernel to initialize the positions of the particles and one kernel to update. So it's operating on the same, like the same blocks of data. It's just that it does different operations. So it's sort of like you can think of it as like a function that operates on an individual piece of an array. Does that make sense? And so based on, one function might be like, I want to clear all this data. One function might be, I want to fill all this data.
And that's different kernels.
Those would be different kernels, correct? So if you had something where you just wanted to clear everything, that would be its own kernel, and you define on the CPU when to execute that. Does that make sense?
So you can think of a kernel as a function, but it's a way to tie CPU code to GPU code.
Yeah, really when it's the CPU code, all it's doing is telling the GPU to run this. And you tell it to run how many times, and you tell it, you share with it these kind of variables, and you tell it where the memory is, the buffers, to operate on.
A more basic question, but
Yeah.
the Unity system is smart enough to realize that if there isn't a GPU, then it's just going to be running the compute shader on the CPU?
No, definitely not.
Okay. All right.
So that's something to consider if you're, as we were talking about, if you're building for systems that you don't really know how, like what capabilities they have, that's something that you would have to plan for, check the capabilities, and maybe fall back onto a CPU system. Yeah, which is not what I'm going to talk about, but it is very important to consider. Cool.
Along those lines, I mean, for the kind of devices, I would probably focus on like it's not PC, it's either a mobile phone or it's like a Oculus Quest.
The Quest, sure.
This is all again everything that we're covering. Will work on other devices.
It'll work on mobile. Yeah, yeah. Modern mobile stuff. Yeah, I was saying I think like I've used it on iPhone 7 and above maybe, although it's not super fast. Yeah.
Could you give a super quick description on what a buffer is and why it's necessary?
Yeah, sure. So a buffer is just a block of data that lives on the GPU, right? So if I create an array or a list in a C# script, all that memory is allocated from my CPU memory. When I allocate something that's like a structured buffer, that memory lives on the GPU. The reason that you need that is because going between CPU and GPU, memory transfer is incredibly slow. You really want to avoid it as much as possible. I mean, going from CPU to GPU is faster, but if you ever have to read back, it's almost, you don't even want to do it. So that's the reason that we basically have to define these buffers on the GPU so that all of our data for the position, velocity, etc., is living there. because we need to be able to access it in this kernel, which only has access to GPU memory in order to update that stuff.
It's a system to expose data to GPU.
Correct. Yeah, that sounds right. It's just, you can literally just think of this as like an array or a list. It's just instead of being on the CPU memory, it's GPU memory. And you can't like loop through it. You have to access it with the giant shotgun approach. Yeah. What's that? Yeah, great question. So we're going to, I can go over that now, I think, yeah. So, let me think how the best way is to do this. Yeah, I'll mention it now, and then we'll go over it again when we're actually building the system. So, like I said, when you dispatch a compute shader, you tell it how many times in each dimension to execute. So you can do up to 3 dimensions. For example, the one I showed before with the texture was a 2-dimension execution. I'll show you real quick how that looks. God, this is very slow. Yeah, so she asked what this SB dispatch thread ID is and how you use it. Obviously, we're using the ID right here, as I was saying, because that ID refers to the index in each dimension that we've executed. So this is just creating a render texture. I won't really go through that. You do need to, if you're going to write to a render texture in a compute shader, you need to enable random write on the render texture. That's just a quick note. Otherwise, you won't be able to write to it. So this is what it looks like when you dispatch a compute shader. And the compute shader is just right here. It's referenced in fill render texture in the script. It's a type. If you go to create shader, compute shader, it's just one of the options. Maybe you didn't notice it before because your brain was just not trying to think that hard about it, which I know a lot of people. When you call dispatch, you have to give it a kernel ID, so that's the first one. It's more clear in future examples. So since this only has one kernel, just calling it for kernel 0. And then it has these next 3 things, which are thread groups, X, Y, and Z. So yeah, that's kind of weird, right? That's where you're giving it the dimension to execute in. But it's a little bit more complicated than that. So I'm calculating thread groups X and Y here, which is the resolution of the texture, X and Y, divided by the number of threads per thread group, which is defined, which has to match in here in the compute shader. I know it's a lot, so I'll draw it out real quick. So if I have my texture, we go from 0 to 512, 0 to 512. You can think about it that way. 511, sorry. Right, since that's the resolution that we've defined, we need to do the thing where we hit every pixel here. So this number basically refers to the number of, does everyone know like what a thread is? A thread is basically just like something that can execute code. GPUs can spin up a ton of them, so that's why they're so fast. This basically refers to how many threads per thread group will get executed, and each one of those threads is going to execute this kernel. Does that make sense? Cool. So the reason then that we do that, we do 8 or like some kind of number, multiple of 8 generally, because that's just like an optimized way to do this stuff. You could have 1 there, and it sort of simplifies this, but it's generally faster to give it more threads per thread group. So if you have 8 threads per thread group, that basically means that you don't need to execute 511 times. You have to execute 511 divided by the 8. Does that make sense? Or 512 divided by 8. Because for every 1 time that you dispatch, it's going to actually break off into 8 threads. So it's not stuff you have to totally understand conceptually in order to use this stuff. Yeah.
So can I just like increase the number of threads like forever?
Yeah, and as we found out with David's laptop, it may very well crash your system.
It diminishing returns anyway, I think. Right?
Exactly,
Just,
yeah.
like, infinite, it doesn't.
And you want to sort of like tune it a little bit to the problem you're trying to solve. Like if you're doing, with this, for example, like if you're doing something like a computer vision algorithm where you want to operate on chunks of an image at a time, you might like try to define your thread group size to be the size of that chunk. There's also some different ways that within a group, threads can talk to each other. Again, a little out of scope of today. Yeah.
So I'm a little confused on thread groups. So you mentioned there's like 8 threads here. Is this 1 thread group?
Per thread group, yes. 8 threads per thread
So
group.
what's a thread group on this image, this 512 matrix? Where does like the thread group come in here?
I mean, it's basically just, it's like more of a conceptual thing, or it's like, I think, a hardware implementation. The most important thing to know is that your number of threads in each dimension times your number of threads per thread group should equal how far you're trying to get in each dimension. You can execute up to 3 dimensions, which can be useful for baking 3D textures. I can talk a bit more later about how to use that kind of stuff if anyone's interested, but right now we'll stick with this. Okay, how are we doing? Cool.
Yeah, this is like stuff that you don't have to like really know. Is there like simple like rule of thumb like thing, like other numbers you can sort of plug in and like assume that they're always going to work even if it's not the most efficient?
I mean, 8 is like the one that starts out with. It's the go-to. So I tend to leave it there unless there's some other issue. I did run into a problem when I was trying to run a few million where I had to increase that number because I was having too many threads out per group. Or yeah. I didn't want to get too in the weeds. Yeah, you're right. Feel good.
We can move on.
Okay, cool. Cool.
Yeah, so the thing that crashed my computer was when instead of 8, we had 128 num threads. So there were 2 spots we had to change the number.
Yeah, it's basically this point and then the num threads, like those 2 spots.
Yeah, so basically like my screen glitched out and then my computer just like completely crashed and it took a long time to come back, like a weirdly long time to come back. So
Yeah.
if that happens to you, it's just like GPU memory stuff.
Yeah, I mean,
You just run out of memory?
I think the GPU probably got over allocated. Lots of fun stuff you can do. There's, you know, a lot less. C# is so managed and like a nice sandbox, but this is like the Wild West. Like, you can definitely. I crash my machine a few times a week for sure. So, possibly per day if I'm really hacking on something. It's fun. It's part of the fun. Cool. So I think that's sort of like that's sort of like the overview of where we're going to go. We can get into more of this stuff as we have questions, as we're building. I think it'll make a lot more sense as we're doing it hands-on. So if everyone's ready, we can do that. Cool. So let's go into the 2.2, build a basic system. And there we go. And you can go ahead and look at the, you can run this, absolutely nothing will happen. This is a completely empty template basically. The only thing I've defined for us is that we have 10,000 particles, but none of that exists yet. So, how did I define? So this is all from scratch. Okay, great.
So compute shaders are not connected in any way to GLSL or GLSL, or all this library that we use to run.
Oh, like Shader Lab, the CG? I don't believe so. It's all pretty much the same syntax, but you don't have to have like the pass and CG, start CG program and all that stuff. I mean, it's the same language. CG is basically a superset of HLSL, meaning it's all of HLSL plus some extra code. It's an NVIDIA library. There's like separate documentation on that if you need to look that direction. So we're going to start basically by creating a list of particles on the CPU, and then we're going to figure out how to render them. Will be how we start. So let's just define a struct here for our particles. And we'll just do these will need to be public, vector3 position, and vector3 velocity. We won't even need that for a little bit, but we'll put it in there anyway because it's useful. And basically I just have this wired up, so in start we're going to call initialize particles. You can use the space bar to reinitialize, and then I have stubs for update and render particles. So we'll keep it nice and organized. All we're going to have to do is put code into these three functions. So first let's figure out how to initialize. So since we're going to do this on the GPU, we do need a way to store that, at least the initial conditions of this on the CPU. So let's just make a new list of particles, type particle that we just created. You can just call it particles. And let's just loop through a for loop. We'll use that num particles that I defined. And we're going to create a new particle is equal to new particle. And we'll set the position equals to, you can use any kind of like random, but I'm going to use random inside unit sphere. It's a useful one. Velocity we can just set to 0. At that point, we will go ahead and add that to our list of particles. So now we'll have this initial condition on the CPU.
Go back up before you define the particle.
Yeah. Simple? Yeah. Everyone there? So now we'll need to create a buffer to store those on the GPU, as we had mentioned before.
Maybe give everybody a chance to copy your code that way.
Oh yeah. Is everyone good on that? Okay. So good. Fortunately, it's going to take us a little while before we get anything on the screen, so the feedback loop will be a little slower for a little bit. So, maybe that's the...
So you included things in there that are just vector 3, right? It's like you want to define an ID for the particles.
Mm-hmm. Yeah, so you can basically put anything inside the struct. This is, right now it only lives on the CPU, but we'll also have to define this same data structure on the GPU, and they will have to match up. Yes.
Is that enforced by the compiler, or it just has to work?
No. So a very common error that you'll see is that you mismatch your structs and stuff is going in really weird directions and you don't know why. So there's a few things to like help with that. One of the things that I like to do is add a static integer here for what's called stride, and I'll get into what that is later. But basically we want to know how many bytes of data are in this structure. So here I have 6 floats because each vector 3 is 3 floats. So I'll do 6 times size of float, and that's going to be the size of my structure in bytes, which is very important to know when you're allocating memory without compiler checks.
Why is it static?
What's that? Yeah. So this is basically size of float is how big a floating point number is in bytes, which is typically like how you allocate memory. Since there's 3 floats per vector 3, you have 6 floats in this struct, and so this is the size of one element of that struct. That's important because when we create a buffer on the GPU, we need to be able to index to like individual indexes, like an array. So this will tell it how big one element in our buffer is.
Wouldn't you also have to allocate a space for the stride itself, like units?
So because it's static, it gets stored elsewhere. So it's not actually an issue. Yeah.
Is that the reason for making it static?
Yes. And also then you can access it statically.
And this is, you're just putting that there for reference?
This is solely for reference. It's a way to keep track of stuff as you start adding more stuff to your structure. It becomes much easier if you are keeping track of that somewhere.
The size of the float might be different on different systems.
That's true.
So
Yes.
as opposed to putting an 8 or whatever that number might be.
Yeah. That's true. He was just saying that the size of float is might be different on a different system, so it's important to use that. You cannot do size of vector 3. It doesn't work. Unity doesn't implement it. Yeah.
Let me try to be smart here.
Yeah. Okay. So now that we have that, we need to define a buffer to hold these particles on the GPU. So as I said, that is a compute buffer, and we can just call that particle buffer. And so now that, yeah. And all that is a reference. There's actually no data stored on the CPU. Okay. So we need to make that into something. So we'll say that our particle buffer equals new compute buffer. Count is the number of elements that we're going to want. So that is num particles. And the reason I made that stride variable earlier is because it also requires the stride, which is the size in bytes per one element of this buffer. And that's how we're able to index into this, this buffer. So we type particle.stride, and that way we've created a new block of memory on the GPU that is the size of num particles, and each element being size stride, which is the number of bytes in that data structure. Does that make sense? Everybody good?
Yeah, does this not, it doesn't figure it out based on it doesn't know any object reference, right? So
Correct,
it has
yeah.
no idea or solid.
It has no idea about anything, yeah. So you have to tell it. Okay, cool. Yeah, that's fine. Yeah, we'll stay here because we actually, since we've created this list of particles, we're going to actually now upload that data to the GPU. Since this list here is currently in CPU memory, we need to get it to GPU. So we do that by calling particle buffer dot set data and pass it that list. And that basically is just going to copy that data from the CPU into that buffer that we just created. And that's why it's important to define your structures properly, both on the CPU and the GPU, because it's literally just copying raw data. It doesn't know anything about what you're sending it. Okay, cool. How's everybody feeling? All right, cool. Everybody good on that? So what we're going to do now is we're just going to render that data that we put on there, or render these particles. We're going to leave out that update step, the compute shader step, because we need basically to get these on the screen. I'm sure you're all getting very tired of staring at a code editor and would like to see something on the screen. So what we're going to do is create a new shader, and we can just use an unlit shader here. Call it particles, maybe. Actually, yeah, okay, cool. Sorry about that. Just making sure I could do what I was thinking about doing. All right, so we'll go ahead and edit this shader together. This should look very similar, so we were just in some of these shaders before. So as I was saying, we're going to have to define that data structure on the GPU. So need to make it match this exactly. So let's just go ahead and under the include UnityCG.cginc, we'll make a new struct called particle. None of the names here matter, but they just have to have the same data structure. But we'll use, I prefer like lowercase sometimes in shaders. A vector 3 on the CPU becomes a float 3 in a shader. So we'll set float 3 position and float 3 velocity.
So I guess order has to matter here, right?
Order absolutely matters because, yeah, otherwise they'll get swapped. So
What type of shader was this?
this is just an unlit shader. Yeah. So that's why usually when I'm writing these things, I'll kind of have them side by side to make sure that I get it exactly right. It can create some very weird bugs that are hard to identify, and then it's something that simple and stupid. Cool. And then we have to also define that buffer. So as I said, in the shader, this is going to be called a structured buffer, structured ed buffer. I guess this may be a little tougher for people without the code highlighting, so let me know if it...
This one actually highlights.
It does, okay. So you add particle, that's that structure we just created, and again we'll call this particle buffer. Cool. Let's see, so basically then we need to be able to know how to, we need to be able to render this stuff, and there's a few different ways to do it, but my preferred way is using what's called indirect instanced rendering. So we're basically going to be instancing geometry. The indirect refers to the fact that all of this data is basically on the GPU and none of it cares. So it's another sort of weird, we're just going to tell the GPU how much of what to do. So let's go into the render particles, and we'll just I need a few more things, but let's actually make this a material first. So right click, create material. It's a great trick, I didn't know. Call that particles. I know how to do that, yeah. That's what I usually do. We'll need to define a material in our particle system. So we'll just add that. Yeah, and that should be good. So that way we can add this here. Since we're going to be drawing from the script, we have to basically have a reference to that. Just go ahead and drag that in. Yep. Just public material mat, yeah, so that I could drag that in. Are you talking about this one? No? In the shader? Render? Yeah, I haven't actually done anything there yet, so. That's
the particle system
just the particles material that we just created, yeah. So we're going to use that to render. So there's a few things that need to happen here. First off, we have to tell the material about the buffer that we've created. So there's this function called material.setBuffer. It's just like setting a parameter from a script for any other type of shader or texture. It's just for a compute buffer. So we're going to tell it that particle buffer should access this compute buffer that we just created. And then after that,
So who's the guy in the string? What is that referencing?
yeah, so that is referencing the name in the shader.
Oh, the buffer that you added to the shader.
Correct, yeah.
And that's how you're tying it to here?
Yep. Basically, all you're doing is you're telling the GPU, hey, this is the start of this data. Like, this is the data you should access here. What's that? Is there a question? Okay. Bless you. And then this is a drawing API that I like to use. Draw mesh instanced indirect. Got a little ahead of myself because we don't actually have a mesh yet. So apologies for 1 second. We also need to tell it what mesh to draw. So we'll define that in a second, just add it for now. Yeah, so you just call it a mesh. Need to give that a mesh. There's like a lot of parameters for this. So I'll just kind of like submesh index is 0. The material we have. You have to give it bounds, which I think is related to occlusion, to culling. You can do new bounds of. It's basically just like a bounding box. I think it would like it would cull outside of that. I just make it really big because I don't want to deal with that. So easiest way to do this is just new bound vector 3.0 and vector 3 of just like a big number. So we'll just do 100, 100, 100. And here's another thing that we need to create is this compute buffer with args. So this is where we're going to tell the GPU how much to draw, essentially. So if we look at this, so that I got also a little ahead of myself. If we look at the reference for draw mesh instance indirect, this args buffer has to be, it's basically 5 uints, and it's also going to be stored on the GPU in a buffer. But it's basically how we're going to tell the GPU how to draw. And the 5 of these refers to basically the index count of the mesh you're instancing, the instance count, which in our case is the number of particles, index start, and base vertex start, which most of this is just going to be 0. So it's not really the one that matters is the instance count here. So let's go back in here and define this, so just make a uint args, so a new array of 5 values. Everyone got that?
Why 5? Because like on this
So-
manual it was 4 that I read.
There's actually 5. I'm not sure. I can't remember what the 5th one is. Like I said, most of them are just going to be 0 in most cases. I don't know. There's documentation for those somewhere, but the one we're really going to care about is this one, which is just going to be the instance count. So, like I said, we also need to create a compute buffer to store those, because basically this is all going to just be accessed directly from the GPU. We can call that args buffer. And we'll go ahead and write, after we do this, we can initialize a new buffer for the args buffer. So this is 5, and in this case, it's going to be 5 uints. So we're going to say 5 times size of uint. And that'll make sure that it's the right size for this array. After we've got that, that's fine. We can, I'll leave this up for a second. We can set the data from that args that we just created.
What was the args buffer for again?
So it's basically like it's going to tell the GPU how many instances of this geometry to draw, and it's going to tell it how big each of those geometries are.
So the first buffer has all the vertices, and this one has how many you're going to draw.
The first buffer has the positions of particles, and this one has basically information about the mesh that we're going to draw and how many of them. Yeah.
What was the type that you're using cost for arg buffer?
It's also a compute buffer. One thing I forgot with this is that you have to define the compute buffer type, and compute buffer type is indirect arguments. That lets it know that like these are the instructions basically. This will all feel like boilerplate eventually. Okay.
And you're multiplying by 5 here is 5 times because of the 5.
Yep, because we're storing 5. Yep, exactly. So again, you have to make sure that all your data is the same size on each side. Yeah. And then, so we need to set up those args. So I'll take a quick peek at these references again. Yeah, so we're going to set the values that we need to set. Basically, this first one is the index count. And you just tell it which submesh. We're just using the really simple thing, so it's going to be the first submesh. So this is the indices per mesh. And then this will be the number of meshes, which is the same as the number of particles. That has to cast to uint. Oh shit, sorry. And then once we have that, since this is only changing on the CPU, we have to go ahead and call setData again. And that uploads the data to the GPU, since that's where it needs to be accessed. How are we doing? It's a lot of stuff. It's a lot of stuff. At this point, I haven't memorized anything. I have a bad habit of rewriting everything from scratch every time. It's good for learning. It's bad for speed. Yeah.
Can you remind us why you're using graph.go mesh instance indirect
Yeah.
and not that instance, or not just go mesh?
You definitely could do that. I know I have a good reason for that. It's just the one. It's one that I prefer to use. The reason that you would use this one is if, like, these arguments would change on the GPU and the CPU doesn't know about it, which is not really the case here. I think I honestly just like the API better, because this makes you provide a list of matrices. Okay, yeah, this is why. So if you look at these, like the API for this, it makes you provide this list of matrices. So for like rotations, positions, and everything like that. But all that data for us is living on the GPU. And so we can't just pass that stuff because it's already like up in the GPU. So that's why we need to use indirect.
So we want instances, but we don't want like matrices.
Right, we don't want to keep that data on the CPU because we're going to be doing all the manipulation elsewhere. You could pass it a list of just like dummy, totally empty stuff and set that later on the GPU. That would be one way to use this API. So you could just send a bunch of like identity matrices and then change them later in your shader. But I just prefer to use this API, although it is granted a little more complicated since you're dealing with that extra buffer.
And if the draw mesh doesn't accommodate these inconsistencies,
Right, yeah. So I forget. And I think what happens if we hit play? I think there will be something. Not at all. Oh, did not set a mesh. We're just going to go ahead and draw a quad here. Just happy little quads. So you can select the quad for the mesh. And look, we got a quad. This is like, if anybody's ever done like an OpenGL tutorial and you spend like 5 hours and then you get a single triangle on the screen. That's what this feels like a little bit.
you can go back to the parts of the plans.
Into the script? Yeah, for sure. Never mind.
So where you're now, the 10,000 watts per hour is in stock.
It's really bad for performance. What's that? Yeah, exactly. Yeah. To this part? Or the data? Do you think, David, do you think you can see it? She just needs help there. Does everybody have a square? No? Oh shit. What's that?
It'll lower the number of particles.
Okay. Are your graphics card drivers updated? Cool.
Yeah, and then CPU setter makes me feel small. So, your particle buffer, is it just extreme particle buffer? I know, I guess that part. Yeah, I haven't, so you I don't have it, I don't have it instructed that far. How are you going to use? Can you go back to the bottom particles? So that I got time to extract these.
Sorry, what was that?
Are Unity's like out of the box particle system set up like this?
So now I think it's closer to this. Back before the VFX graph, everything was like CPU pretty much. That's not 100% true. I think it was maybe around like 2017 or something. They started adding GPU particles. But yeah, there was definitely a time when you kind of had to do this stuff yourself if you wanted to do these. And I still chose to, like, it's still more flexible to write it yourself always. I do a lot of stuff that I can't do on VFX Graph. It's just not actually possible, but that's like what I like to do. So most of the stuff, like everything we're doing here today is like pretty easily implementable on VFX Graph. Yeah, so the intent of this class is not to give you something that's going to like be better than what you necessarily can do already. It's more just to learn about how these systems work and feed your own exploration, because there is a lot of stuff that you can do that VFX Graph would not cover. But I'll sort of leave that to you guys, since obviously it's a lot to work up to even a simple thing, so, yeah.
VFX graph is also, is it still not performant for mobile?
No, I'm not sure. I think it's probably about the same kind of deal, because it's all built with compute shaders, so it's whether the devices can support it or not. Yeah. There's a lot of issues on mobile, not just shaders. So I hate working on mobile. it's a pain. There's like so many weird optimization hacks. Okay. Everybody, what's that? No. Okay, so everybody's sort of got a square. So yeah, well put. We have 10,000 squares. They're all on top of each other. So we need to access that position data that we've like loaded onto the GPU. So the nice thing about using instancing is you get what's called an instance ID. And that's something that we have to add to our app data struct. And we're going to add it, and it's just kind of going to magically get put in. So we'll add a uint, and I call it a IID for instance ID, and you define it as the semantic SV underscore instance. I can't spell. I think it's like that. If that compiles. So that's basically going to tell us, we're drawing this 10,000 times. Each of those 10,000 objects is going to have an ID. That gives us a great way to access that data buffer that we just created. As long as I spelled that right, I think I did. Underscore instance ID. Yep, looks right. Cool. So we have our buffer in here. We have our particle struct. So all we really have to do is like add that as an offset, the position. So we're going to sample that array for particle P equals particle buffer of v.viid. Sorry, IID. So we're accessing the particle buffer at the index, which is the instance ID of this mesh that we're drawing, yeah? And all we're going to do is add p.position to that vertex. Plus p.position, yeah. So that's the position that we defined when we initialized initially. And
So what is v.vertex in this case? Like what is it, just 0?
v.vertex?
Yeah.
Well, it's going to be the vertex position of like each corner of the quad. So, so basically we're just transforming it. Yeah, exactly. What did I do? Particle. Oh, sorry. That's supposed to be lowercase. Some bad. Yeah. So that's why I wasn't compiling. We'll go ahead and fix that and hit play. And hey. Yeah, absolutely.
Where was the actual linkage made between the compute buffer and the structure buffer? Like how does it, in the shader, how's it actually accessing the same?
So that was, sorry, it's a little hard to see with both screens here. Let's see. That was down here where we tell the material mat.setBuffer particle. So that
just has to match the main.
exactly, yeah.
The remaining particle buffer, it just has to string. That's
Yep.
what we call it.
In the shader, yeah, and that's the same way that you would pass a parameter to a shader, like a floating point. You know, if you wanted to like script a variable that would be in a shader, you just call material.set something. Yeah.
Does everybody have
What are we actually looking at now? You said
So-
like take around it and it just disappears.
Yeah. So yeah, it's like this. Is that? This seems a little strange. Did I do something weird?
no, fair enough. Let's teach you guys to maybe go on the backside.
Okay.
It's basically a sphere of squares, right?
It's a sphere of quads, yeah. So if you want to see a little bit more, we can actually do this and like put a cube in there. It'll be a little more, give you a little more geometry to see. Cube of cubes. It's very ugly because it's completely unlit, so it's really hard to see.
So even though they're still on top of each other, they will change their position at some point.
What's that?
I was wondering why they were no longer on top of each other.
Yeah, so up here where we access that particle buffer, and when we were on the CPU basically, and we filled this particle buffer with position inside unit sphere. So that's basically just a value inside a sphere with a radius of 1. So that's why they're sort of just distributed as if they're inside a sphere.
Can you scroll back to start?
This side?
Shader. Go back to start. The shader. I think the tool was.
And if we try to get ASV underscore instance AV without having instance anything, will it errors arise?
I think it would always be 0 maybe. I'm not 100% sure. It probably just wouldn't really set. Yeah, it'd probably just be 0.
Something weird going on with the structure buffer.
With what?
Something weird going on with the structure buffer.
Like it's not working?
Says something like a syntax error. I'm gonna fix hold.
No, don't worry. Okay. Does everyone have that sort of working? Yeah. Woo-hoo. Good work. All right. That's a lot of work to get 10,000 cubes on the screen. But the good thing is it's the exact same amount of work to do 10 cubes as it is to do 5 million. So it's really like great returns on investment in my opinion.
So to be clear, up until this point, all these things can be done using like a C# VB script, right? You can do this entire thing in C#, but much less efficiently.
Yeah, I would say you can do everything.
But it just doesn't happen as efficiently at all because it's all being done in CPU system
Right.
rather than GPU.
I mean, right now we're pretty much just using the CPU since we initialized.
Sure.
But the next part of this lesson is to add some motion, and that's where the returns will be crazy.
So what kind of things that within this shader we can do that would actually turn us like being CPU bound in like say an app or like a mobile app or something? So like let's say we're like if we have like 5 million quads, would that actually like create like I guess a CPU bound problem where we're just kind of like running CPU too much or something?
If too many quads, it's like the issue is going to be GPU problems.
Oh, GPU.
Yeah.
Okay, cool. So
Yeah,
Yeah.
having that number was.
So
Try.
what's like the magic number on like I guess like an average mobile device? I guess is there that we could just work with?
I made a version of Cosmic Sugar for the Quest that has 50,000
I would
particles.
download like an absolute secret.
100,000?
Yeah,
Okay. Write it down. 1,000.
that's for VR though, so
So sad.
that's 2 screens plus like
Yeah.
the stuff going on. But I don't know, you gotta feel it out basically. It's like
Yeah.
you push it as hard as you can and texture and mix and pull back.
Yeah.
And some things will depend on that shader as well. Like if you're pulling up too transparent or there's some complicated lighting stuff going on, like that stuff will
Yeah.
come into play.
Cool. So I'm going to go ahead and change that back to a quad, but one thing that's very useful with particle systems is you want the quads to basically face the camera. It's like a billboard, which I'm sure you guys probably used for some stuff or another. But we want to basically do that in the vertex shader. And I'm going to actually just copy this, I think, from another complete shader that I have in here. Since we're...
If you use the Unity particle system, if you notice, it's like wherever the camera goes, like, the particles aren't going to do what this is doing, which is them go around the backside, they disappear, and then, it's like they're just like always facing you, and not, just, even though it's a hat, it works great for lots of things. Like if you have a gradient, if you have like a circle, and it's unshaded, an unshaded circle is going to look like exactly the same as an unshaded sphere. An unshaded circle that's always facing you is going to look the same as an unshaded sphere that you move around. It's the same for like if it's a gradient. It's like works great for smoke. If there's smoke and it's animated, like you're really going to be able to tell as it happens. Like that's so it's a hat, but a really good hat, and for certain kinds of things. It's like, it's not like an old technique that people don't use anymore. It's still used all the time in particle systems.
Yeah, cool. Sweet. Let me move back to that. Sorry. So we want to basically... Man, all this is from scratch. Oh. we want to create a rotation in the vertex shader that's basically going to align the normal of the quad, which faces directly out of it, to the camera. So what we need to do that is basically just draw a little picture, but basically we have a quad like this with the normal vector pointing out of it, and then we have the camera somewhere here. That's the camera, I guess. We basically need the vector between these two and that, and we're going to do some operations on it to find the rotation between those two vectors and rotate the quad back to match, if that makes sense. This is stuff you can definitely just Google and find like the example, but I'm going to run through it because I think it's useful and it's good stuff to know about. So what we want to do, and I'm going to reference this script because I already have it, basically want to get the vector from the position to the camera. So we're going to get P to cam, float 3, it's going to be a float 3 vector, equals normalize of P dot position minus world space camera pose. So I'll unpack that a little bit. World space camera pose is provided by Unity. It's a built-in variable. It's the position of the camera in world space that's actually rendering the scene. P dot position is the position of the particle. And normalize is going to turn that into a normalized vector, which means that the magnitude of the vector is 1. Normalized vectors are pretty much what you want to use whenever you're talking about a direction without a magnitude. Because it's been a while since I've taken linear algebra, but it's just what you need to use when you're talking about a direction.
Which, if you have like multiple cameras running, which I feel like happens a lot, what camera is this going to use?
It'll be whichever camera is rendering
You
this.
have camera and camera though, right? Like if you have like a mini map or something, for example, that's like a camera and a camera.
I mean, it's whichever camera is running the render on this material, basically.
Okay.
So it could be multiple cameras,
It's like
right?
whatever the current camera
Yeah.
is in the frame that it's rendering.
Whatever the camera rendering this object is, yeah. So have that, and then we basically need to define the normal of the quad. And this I'm just going to set, kind of like hard code it, because it's easy to do. Basically, it's going to be one of the axes. I'll just tell you right now that C forward at 1 is going to be the one you want. Then we need to get the angle between these vectors. That's done with arc cosine of the dot product between them. That's the magnitude of the angle. And then the axis of the angle, sorry, that should be, that's what I get for trying to cheat my way through. So that's the arc cosine. It's not an inverse cosine, but it's sort of how you go the other direction with a cosine to get an angle, an angle back. And the dot product between two vectors is basically the magnitude of the angle. And the cross product to define the axis. The cross product is basically if you take two vectors that are, so we have our two vectors like this, one like that, one like that. The cross product is going to be the vector that's basically perpendicular to both of them. That's just a helpful thing to know. Yeah, so that's how we create a rotation. And then apply it, we need to create a rotation matrix. So I've included some helpful matrix functions. If you include this shared and then matrix .HLSL. This has a few matrix functions in it. I'll go ahead and open that up and show you guys. So, do people kind of understand like rotation or like how matrices can transform vectors or to some degree, right? So like basically, if you multiply a vector by specific forms of matrices, it can either scale the vector, rotate it, or translate it. So basically, to do a translation, you need all three. I've included some helpful functions in here for creating those matrices, so creating a scale matrix, a translate matrix, and then two different ways to create rotation matrices. And then I sort of created this one function that we're just going to use here, which is a scale, rotate, translate, and that basically creates a full transform matrix in that order. So basically, it has to go in specific orders, or else you'll get a different transformation. And this is sort of like the most coherent for this type of problem. So we're going to define a transform matrix. Float 4x4 is a 4x4 matrix. And we're going to use this function, scale, rotate, translate. For scale, let's just give it, since those were kind of too big, let's just give it like 0.2, 0.2, 0.2 or something. Maybe that'll be too small, I'm not sure. Then we use the angle and the axis that we just calculated to create the rotation matrix. And finally, the amount of translation we want to do, which is just the p dot position. Cool.
Where are you getting this?
Sorry, which one?
The three that you're plugging? Where are you getting
This one?
Yeah, where are you getting
I'm just kind of making this up because they were all overlapping each other. I just want to make them a little bit smaller. We'll work on scale independently a little later, but. And then we're just going to apply that to our vertex. And since we've already baked in the position to that rotation matrix, we can take this out of the vertex. And if that is all done right, then that should basically give us what we had before. But pointed towards the camera so you can rotate around. Yeah, that's cool. Is that high enough? Yep. I'm just going to go ahead and see how this goes. If it all compiles, sweet. And if you got all that, then go ahead and hit play. And we'll see what happens. So, looks about the same. But now we can rotate around it. And they're not cutting out. Amazing. What's that?
This is rotating as we move our camera around.
Correct, yeah.
Quick question, when you publish, is there anything special you have to do? Because I know you have to like include shaders into like the publish build or whatever, right? You have to, is there anything for like, for example, the matrix library? Or is it just going to be built into the, okay, so it'll know where it is?
If it's included, yeah.
Where you can include things, but it's only anything special to a certain extent.
Yeah.
For the most part, you don't have to worry about that.
It's It's like as long as you're referencing your shader, either the shader directly or a material in the inspector, then it'll know to pull it in. The only time I've run into that, I think, is if I access a shader through a file system without,
Right, exactly.
yeah,
Yeah. So it has to be.
which, God, that took me forever to figure out. Okay.
Even though it's a quad, because the particles are rotating.
What's that?
Before it was a quad, we turned around, we didn't see it.
Yeah,
But now, because each one's rotating.
exactly. So they're going to follow you, like the Mona Lisa. So you can rotate around. Does not look very good right now. So let's go ahead and like make them look more like particles. I think I'm getting to the point where we need to start having some fun.
The scale didn't seem to do anything.
It didn't. You're right. All right, good. Thank you. Thank you. I needed that. You are quite correct about the scale, and scale that. Unless this is like very small. Yeah, I think they're just really big. So you may want to play with that. In fact, why don't we go ahead and make a parameter up here? So I'm just going to add scale up here, and that'll be float, and we'll just make it. Actually, I like range maybe. Is that how you do it, range? Okay, we'll just stick with float. I like to have a range sometimes because if you go too big and you have a ton of particles and they're all stacked on top of each other, your computer will crash. So we'll start there. We have to define that also in here. So float scale. Yeah, it's just like how we were doing it before in the other shaders, and then we'll go ahead and use that in here. In the, so you'll need to define it up here. This is going to create the editor property, or the way to access it in the editor. And then you also just define it below here somewhere. And then, yep. And if you go back, then you can, make it, yeah. That's starting to look more like particles.
But then where do we actually apply it?
Sorry, yeah, in that vector 3 where I just put the numbers before.
Oh, okay.
You just add the scale in there. Maybe you want to add a range. Maybe you want to add a slider. I like sliders. That's how you do that.
How did you do this? Oh, range.
Yeah.
It's like
It can be good with these systems because, like I said, if you make stuff really huge and they're all on top of each other, it really kills your GPU. So, yeah. But I also like my particles round, so I think we should do that now. So, you'll remember the distance function that we saw in the shaders before. We're basically just going to do something just like that, but apply it to the alpha channel. So we can kind of get rid of this fog stuff. Gonna just get rid of this texture sampling. At this point, you could use a texture on all your particles if you wanted to, but I prefer to go textureless. I'm just going to make them all red to start out. And then what I'm going to do is get the alpha channel and make that UV text. I'll explain what I'm doing in a second here. Oops. What? Okay. Great. So that's kind of the opposite of what we want. So I'm going to sorry, I'll put this up in 1 second. Okay, cool. So here's using some of those same functions that we saw earlier. Basically what we're doing is, so the UV normally goes from 0 to 1, but we're going to subtract by 1/2 and multiply by 2 to get it to go from -1 to 1 across the quad. And then we're going to take the length of that and use that smooth step function, which creates a value from 0 to 1 interpolated between that 0 and 0.2. Which is going to give us like a nice fade out, which is nice for particles.
So this is inside the core fragment.
Yeah, so this is just in the fragment shader. So it's just like what we were looking at before with those functions defined on a quad. It's just we're doing that for all these hundreds of thousands of quads.
You got the particles to actually like dispersing around.
Yeah.
Like what did you do for that again?
So that was in the particle system basic, the C# script, where I set the position to random inside unit sphere. Yeah.
Can you explain what's happening in that line again?
Yeah.
When you're
So,
thinking,
yeah, so maybe it's better if I break it apart a little bit too. So I'll usually name this ST. So basically like, if we're looking at a quad like this, 0 to 1, but we want to make a circular thing, so so like this is the origin, if you will, at 0, 0, but we need to move the origin here. So we need to shift the values so that it goes from -1 to 1 and -1 to 1 this way. Okay. Does that make sense? So that's what's happening there with the 2 times. Basically we're subtracting so that it's -0.5 to 0.5, and then we're multiplying by 2 to make it -1 to 1. So I call that ST when I'm doing that. That's this stuff. This kind of stuff is very common in it's called like distance functions. So you'll often want to know how far you are from the center of your quad, and you can define basically shapes based on that.
So when you do that, though, what are we seeing? It looks like a
Yeah.
black square with a red dot in the middle.
Yeah. So that's because that's too much.
And I can see red, it looks like there's a couple of red dots in there too, or is that just the red dots behind it?
It's probably just the ones behind it. So that's because we need to make this a transparent shader. Because right now it renders all the black. You know, you could run this as a particle system, it just would not look very good. So let's go ahead and do that. We change the render type to transparent. And we have to add what's called a blend-in function. I won't go too deep into that, but I'm going to go ahead and do blend 1, 1, which is additive blending. That makes stuff really pop when it, like, stuff that's partially transparent goes on top of each other. It, like, makes it just, like, a lot brighter. So, make sure that, yep. So, that's all you really have to change. You know, we were talking about transparent shaders earlier. This is how you do it.
This blending, when I was doing some inclusion work I was doing, there was some along the line with that, or some blending stuff going on as well.
Yeah, yeah.
Oh,
Can you go to line 88?
Of this one?
Yeah. Great. Thanks. It's missing something on that book too.
Okay. Yeah, so all these lines in the fragment shader, that's basically just defining defining that circle procedurally. So we don't need to use a texture or anything. And it's also nice, it like anti-aliases and it like looks good.
it's a little more expensive though, right?
I think that's a little up for debate. I think I mean, you know, you have to really test it at scale to notice a difference. And David's, I think, tested it with quite a lot. He said it's maybe a little faster. You had to use a texture. This is kind of convenient for me. And I mean, I just tested this system running like 8 million particles the other day, and it was fine. So.
Sure. I mean, if you're doing a transparent texture, you also have to use a PNG, so you get less compression too, right? So
right. Yeah.
you're saving on that.
Yeah. So I mean, you know, mobile, for example, you want to like really minimize your textures, right? So.
For sure.
Like anything in software development, it's like knowing your requirements and fitting the solution to the job, I think. Yeah. My solution, yeah.
Quick, I have a question. I see the black is gone, but my game view is still there. That one.
Yeah. So like if I turn on a skybox,
Yeah, it is. It's not kind of like.
yeah, great point. So that's because of the occlusion. So what you have to do to fix that is you go up here and you say Z write off. So what that means is it's not going to write to the Z buffer. So that way it'll draw something, you know, if it draws one thing, it's still going to draw everything behind it. Normally if you draw one thing in front, the stuff behind it would just get totally ignored.
You still see the square, you change it to like both, just to see the.
Yeah, and then also something to add here is cull off. So that way it renders on both sides like we were talking about before. So if you have Z-write, yep, Z-write off and cull off, then it's going to start looking a lot more like particles.
What did the call off do? Because it doesn't look like, I spin it around, I guess you don't need.
Oh yeah, good point. Yeah, sorry.
Because it's rotating.
Good point. Yeah, because they're billboarded. My mistake.
This happens, takes 2 hours to do something. Now I don't even see my game view.
Yeah, now it's
Is it just the camera's too small?
Oh, weird.
No, I don't see it in my game view either.
I think if you make it black, I think they're maybe just kind of, the camera's far away.
So they're not rotating. The background black color?
Yeah, I think they're just kind of far away and small.
I think you actually can. Make the background of the camera black.
Cool.
And I brought my camera even pretty close to it. I didn't see it before.
Oh, really? You good? No? You don't know what's...
It's there, right? It's in a whirlwind.
I just want to talk about this thing called overdraw really quick. So if you have a sprite that's this big, and then this is your quad, and then the thing that you're actually drawing is this big, you're going to wind up with a lot of transparent pixels. And then what happens when you render, basically any pixel that's transparent, like it still renders it, it still looks at it. So if you have another quad over here, like they are apparently not overlapping, but they are overlapping. And especially as you add like more and more particles, if they're transparent and you're getting, if you have overdraw happening, things are going to get real slow once you start getting thousands of these things on top of each other. So you do have to like balance the size of the particles to maintain good performance. And one really good way to do that is to make sure that whatever you're drawing is as close to the edges as possible. So having like your drop off like go right to the edge is going to be a lot more efficient than having any transparent space there. And if you want to avoid that problem, then you don't use transparent sprites at all.
If what?
If you don't want to have that particular problem, then you don't use transparent sprites.
Is that why so many of those like dust particle effects are quads?
Yeah, I mean, if you want something to be dusty and semi-transparent, then it should be a quad, generally speaking. Yeah, if you want to display a texture, the quad's the way to do it.
I can't probably explain that. Because this one is working, so this is not this setting. That's so strange. At least, yeah, the next, when you go into the next section, you come back up. Yeah, maybe the next time you write it, it'll work.
So these particles are all Cartman squares, essentially?
Correct.
Why is that? Where does that mean coming?
So the quad is the mesh that we're choosing to draw.
Okay.
We were drawing all the sides of the shape, drawing cubes, so you can draw
But
cubes as well.
if it in the
That's in the script.
it was in the part, yeah, if we just made this a sphere, would that be?
You can do that, yeah. The spheres that have a lot of vertices, so you won't be able to draw near those many.
So in the situation, in that case, even though it's like we're like basically making all the like the little dotted line transparent, but it's still really there, is there anything?
Yeah, yeah. So this is sort of
So
how
I just dropped that, I use the material, I just dropped a picture onto it.
yeah, so
It's
that
cool, you can kind of see it, like you see the picture like kind of in there a little bit.
because you
It's
multiply by this.
like cat.
Nice. Yeah, exactly. So if you want to make some cat particles.
These cameras, these are this is a picture I have on my desktop.
How do you do it? Do you put the
I
cat
use-
on the quad that you have?
No, I put it in the shader.
Oh, in the main
I blended it with the I added it here, and then I blended it with the color red. But it's still there.
Of Tetris effects.
I'm not sure.
Okay. It's like, yeah, basically particles everywhere. I'm wondering if that's like possible to do on like something for a PS4.
Yeah, I'm sure it is. If you can think it, you can make it.
No, I just added it together here.
Okay, cool.
Before it says she fix 100.
Does everyone sort of have a particle system? No? Do you need any help? What's that? Oh shit. Sorry. Okay, cool. Well, there's still stuff like that is totally working that's in the repo, so be able to like play with that and read through it.
What I want to do is I want to look at it tonight when I've got a chance to see it, figure out what it's used for.
Definitely. Feel free to email me if you have questions after that or whatever.
Because I can listen and follow along.
Okay, cool. Yeah. It's
hard to keep typing in there.
yeah. I know it's like a lot of information. It's a big topic. So it's something, yeah, I'm trying to figure out how to best present.
So one thing I noticed, I don't know if this is on purpose or not, but it culls the things behind the transparent square.
Yeah, so that was not really on purpose. So if you put ZWrite off as one of the directives, that basically prevents it from writing to the depth buffer. So it won't do any culling based on the depth.
But then it doesn't work with the skybox.
Oh, is that right?
Apparently. And I'm not quite sure I understand why. The version I have that's in the next section, it does work with the skybox. I just checked it. So it might be something to do with blending, yeah. Those are the kind of things that are very like subtle graphics bugs that it's only experience and like racking your brain and finding some weird obscure forum posts to solve, basically.
I love those obscure forum posts.
Yeah.
Blend, shader, Unity. That's
As long as there's an answer, I like
Yeah, it's just a question and no responses.
from 5 years ago.
Yeah, I got the answer. It doesn't say what it is.
Exactly.
One quick question.
Yeah.
I get a couple warnings that say your architecture is supposed to have completed a buffer, and then they're recommending you use
That's
completed buffer release or disclosed.
yeah. That's a very good point, and something that I have in my other systems, but we didn't do on this one. So typically, it's best practice, and yeah, you'll get a warning if you don't do this. So on destroy method, you would want to dispose of these two buffers that you created. So check if particle buffer not equal null, not equal null. Particle buffer dot dispose, and we'll do the same thing for the args buffer.
Like when I try to set a skybox on,
It's good to always dispose of your memory, and since you're allocating, especially if you are creating these things on the fly, you'll definitely need to do that. Since this is just like we're running it and then we're turning it off, it matters a little less, but it's good to do that and get in the habit of it. On destroy is called when a game object is destroyed. So in this case, it's just sort of when we stop the program.
Okay, so in this case, it's not.
Correct. So.
it's also valid.
I think I know the problem with the skybox. I think that you have to add this q equals transparent, because that way it'll get rendered after all the solid buffers, because this skybox gets rendered on top of everything, sort of, so I think that might do it. Yeah. Just the wrong order. Yeah, exactly. Yep, that did it. So yeah, so basically had to add q equals transparent. That makes sure stuff gets rendered in the right order, because basically the skybox would just get input on top of the particles.
Can you just for like 2 seconds explain what the render queue is? Because I feel like I've run into this before and I have no clue what it is.
Yeah, I'm sure there's some very in-depth Unity documentation, but essentially objects are rendered in order. So there's basically like solid geometry gets rendered first, and that gets rendered to the depth buffer, and so that way it can occlude transparent objects, so and other objects. So then after all the opaque stuff is rendered, then the transparent stuff is rendered and blended on top. So I think what was happening probably is that the skybox is in the solid buffer and it must write the Z buffer really weird, and probably because you're inside this sphere, right? Like it probably the backside was covering it. I'm not really 100% sure why that doesn't work, didn't work, but yeah, that puts it in the right queue, and you can actually control that in shaders. This render queue here.
Yeah.
So if you're ever having like Z fighting issues with sprites and stuff like that, you can like be very definite about where in the queue it's going to get set. But these are like the typical ones. You'd pretty much just use geometry, alpha test, or transparent.
Every time I've ever tried to mess with this, I broke it, so I just leave it alone.
Yeah, exactly. It's one of those things, you try it until it looks right, for sure.
Did you have to do any disposing on the shader side after you created the on-destroy in the particle system?
No, that's all. Yeah, you need to handle all that.
Is this correct for the particle system? C# app? It might not be like releasing yesterday. It might not be like super dynamic. So actually, yep. See? So yesterday I was like, if you have 1,000 particles, I have 1,000. You have the correct particle. Where's the particle struct?
I don't know, I think I divided it.
So you got that, right? And then the structs. Okay. Okay.
All right, I think if everybody's sort of at that point, we can start to add some motion. That would be good, yeah? Cool. So basically we have the stuff on the left, we have the stuff on the right, so we just have to get this stuff in the middle now, the compute shader, which is what this is all about. Yeah. So everyone, yeah, take a breath. It's okay. It's going to be fine. If you right-click, we'll create a new compute shader. And we'll just call that update particles. And we'll open it up. And this is what you get when you have a new compute shader. Essentially, it's set up for writing a texture. We don't want that. We don't care about that, because we're going to deal with our buffer that we're defining. So we need to, again, define our struct in here. That's like that basic one we defined in the other. It's defined all the same everywhere.
It's not opening up right now.
The compute shader?
The creator is like, hey, my tab's crashing.
If you go into just open Visual Studio, maybe it's got a dialog box open. Sometimes there's dialogue and
Try to do that as a whole thing and see if it works.
Open VS first, and then open this project.
cool. This won't be too complicated, so it should be pretty quick to catch back up. So this is read-write texture 2D. That's like what we had before when we were filling a texture, but what we want here is read-write structured buffer. This is a new type of type particle that we defined up there. And again, we'll just call it particle buffer. So again, these are going to be the same buffers that's shared between all these different shaders. It's all just staying on the GPU, and they're all going to know where to find it. We can get rid of the result. We don't need it. Get rid of this code. So read-write structured buffer, same idea, but you're able to write to it. So yeah, kind of proof is in the name there. So when I was talking before about the different dimensions and how the 881, that's basically the number of threads per thread group in each dimension. Since we're just working on an array that's a single dimension, we don't care about executing multiple threads on the y dimension. So we're just going to change that to a 1. So that way we're going to have 8 threads per group in the x dimension and just 1 in y and z, since we know we're not going to go in either of those other directions. So let's see. Cool. So we're going to basically start by getting our particle out of the buffer. And we'll access that as id.x, which is the ID in the first dimension. Since we only have one, that's the only one we care about. And at the very end of our shader, we're just going to write that back to the buffer. And then in the middle here is like a to-do. Move the thing. So let's try something just super basic and easy right now. We're going to set the velocity of each particle to a constant, just like a small upward motion. And then what we want to do here is called integrate the velocity, or the position, which is basically just updating the position by the velocity times delta time. This variable does not exist yet, so I'm going to define that up here. It's something we'll pass in from the CPU. dt is delta time, so the change in position over time is the velocity times the change in time.
Can you not access time per
You can actually, so let's see, what was the, we can try that and see if that works. I think it should. Is it delta time? Did I get that right?
Looking up.
Okay. So as I mentioned, I think in compute shaders, they should still be available, but you will have to define them in order to get access to them. So we'll try that. All right, so that's like a very simple kernel. All we're doing is we're setting the velocity, and then we're going to update the position based on that velocity. So this is going to basically get executed for every single particle individually. And now we need to write some C# code in order to actually do that. First, we'll need to define a compute shader. Shader, yep. And don't really need to do much with that. We just have to execute it on update. So this is getting called in the update loop. We'll have to set the buffer, same as we do on the other ones. It just tells the shader where to access the buffer. We have to give it the kernel index like before. We just have one kernel here, so we're just going to give it 0. And then we set particle buffer to particle buffer. Cool. And then to execute that, we call shader.dispatch. We give it the kernel index. We give it the threads in the x direction, y direction, and z direction. All we care about is x, so what we want is the number of particles divided by 8, which is because we have 8 threads per thread group, so we're just going to divide the number of particles by 8, and that should execute on every single particle. In the other dimensions, we just want 1. If you put 0 there, nothing will happen. So you need to at least have dimensionality to it. The shader? Yeah, it's just called a compute shader. And that needs to be public so that we can put it in our editor. And then we have the shader there, so we'll just go ahead and drop the update particles shader into our shader variable in the inspector. And then, if everything is done correctly, seems to not be.
Is shader the compute shader?
What's that?
What is shader?
Yeah, it's the,
Public, okay.
yeah, so that we could access the compute shader. And I seem to have lost my particles, so let's see what's the problem here. So I'm thinking Unity delta time is maybe not the way to go. Let's see. Yeah, that makes them disappear completely, so Let's go ahead and put our own dt in here. So I'll just add float dt, and we're going to multiply that by the velocity. So right before we dispatch the shader, we'll want to call shader.setFloat. You don't need to give it the kernel ID here. Just pass it the name dt, and we'll do time.delta time.
This is in the update.
What's that?
This is in the update particles.
Correct, yeah. And let's see if that works better. What's that?
The old vector imports font now.
Oh, really? Oh, interesting. Ah, because this is supposed to be plus equals, sorry. I was just setting it equal to the velocity, so they were all just getting set to 0, basically. my bad.
Position or
Yeah, the position should be plus equals velocity times delta time. Yeah, there you go. And spacebar will reset them, so just if they start flying off the screen, you can hit spacebar to reset. So yeah, that's it. We did it, guys. We got here. Yep.
Does anyone else do garbage collector warnings?
Yeah. Is there a function in the shader where when you say velocity times delta time, can you like do times random or something like that?
Like random velocity?
Yeah. It's like a random, because they can go up at different speeds or whatever.
Totally, yeah. So we're getting there.
Okay.
This is pretty much like the baseline. Anything that happens in this section is sort of like where the magic happens. So, this is like where you can calculate new forces and add all sorts of stuff. So
there's all that same level of like Unity functionality in the shader here as well?
Yep. So the system that I have, that's the complete system in here, is like pretty equivalent to what you might see in like VFX Graph. So you'll see sort of like a way of how you would build that up from scratch.
Some strange reason I can't open a cube shader in Visual Studio 17, but I can in Angular.
Strange. Sorry, I can't help you debug Visual Studio.
See Visual Studio though, but it
Yeah.
works.
So was it create the kernel, or because I get kernel versions in the shader?
So that'll typically mean you have a compiler in your shader. So if you open up the compute shader and kind of like hit space somewhere and save it again, that should force it to compile. So like for example, if I put something in there that's not supposed to be there, then it mine are like not.
That was a very existential explanation there.
Yes, my problem was here is when it comes to moving the shader
Yeah,
versus
so
the particles.
if you sort of like go in here and go into the shader and resave it, it should compile and show you errors. Are you getting compilers?
No, I don't get the main errors from the console, only when I run it.
In the compute shader?
I'm assuming so. I didn't say anything about that. Oh, did you send the compute shader in the only there so
I don't know how to use the gig ray.
It's even easier. You're doing it the hard way. And
I
look at this guy. Hell yeah. Got Vim hooked up.
oh, I don't use Vim. No,
Oh, okay.
no, I'm not that hardcore. I use Nano
I worked with a guy.
because I don't know how to get out of Vim.
And I'm like, why?
No, it takes me too long to get out of Vim. Yes.
I got my particles, layers, kinetics, there. There's like a and then
We should do that.
here.
This is a much more quality.
You need the Octopush shader set, or the particle system. So yeah, so I would say software test just say that there's different particle sizes. But double check the audio strut, and then so then check out the PCA. So loss equals 1,000 times 1,000, and then if you want to add the velocity, set it equal to 0, basically so it's 0 right there. So now if I push it, I need to extend
Anybody okay?
It looks like you did this one.
Also, if anybody is totally lost, I just pushed this where we're at. If you want to pull, if like you need to pull and like get the latest to get caught up. Yeah. What's that?
So I'm getting a feedback here, and basically
So it's going to be some kind of compiler and then a compute shader. So if you just hit a space, save, and then go back, it should, yeah, there you go.
This requires that the GPUs don't overload.
That forces it to compile. I think this is just maybe a typo. The variable name. Yeah. So yeah, if you like just edit, if you just resave a shader, and it'll recompile it. Yeah. The day.
Like he's got more safe and stuff on the X. Yeah.
Okay, cool. Sweet. Everybody's there? Yeah? All right. I think, how long am I supposed to go? Until like 6, 8? What is this scheduled to? Okay, cool. Sweet. How long are you guys expecting to be here? 7?
Say whatever you want. I'm here for it, man.
Great.
When do we start opening beers?
Yeah, ooh, that's a great question.
So yeah, maybe after we force the like spend a little time messing around.
Yeah, I think that's a good idea.
Drink some beers and then you can go into advanced mode.
If I drink too many beers, I'll really get moved myself.
He's writing it from scratch, man.
All right. Anyway, sorry, that's not appropriate in the slightest. Cool. So I'm gonna go ahead and add like an attractor force because that's something that is like really nice to have. You can start to do a lot with that. So let's go ahead and we're just going to define a transform that's going to be our attractor. Yep. Easy enough. So an attractor is essentially just a position in world space and then a strength. It could be positive or negative based on whether you want to attract or repel particles. You can get a little more fancy with like fall off and stuff like that, but for now we're just going to have most basic attractor, which is a position and a force. So we're going to have a public transform for that. And in update particles, we're going to pass that data to the shader. So we're going to do shader.setVector. This is for the position. We'll call it attractor pose. And that will be the attractor transform dot position. This is all in world space, by the way, so we are always using world space positions here. Now we're going to do shader.setFloat. That'll be attractor force. And we're just going to make a new variable for that because I forgot to make one. Attractor force. Just generate a new field. If you didn't see that little shortcut, all that's doing is creating a new attractor force here, and that'll have to be public. So we'll have a transform and a force that's public, and then we share it like this with the shader. So we'll go ahead and put that in the shader so that it can access it. So we'll have float3 attractor pose, and we'll have float attractor force. So this is, people were asking about how you share data with the GPU, like this is the way to do it. Anything that like you want to become interactive, this is where you're like sort of passing the information. So then in our update kernel, we're going to define a new force to apply to this particle. We'll just start it out at 0. And then we're going to add getting ahead of myself a little bit. In order for an attractor to basically push or pull from a particle, we need to know the vector between the particle and the attractor, right? So the direction from the force to the particle, and we need to know sort of how far away that is. So luckily we already know the position of both. So we're just going to make a float3 vec to attractor equals p dot position minus attractor pose. and we're going to make a normalized version of that called dir, and we'll just do normalize back to attractor. We'll also want to know the distance, which is the magnitude of that vector. So we'll just find the distance, which is length of vec to attractor. And then from that, we can calculate a force. So we're going to do force plus equals, so it gets a little tricky. We'll do 1 over the distance cubed or distance squared. This is sort of like up to you. It's like a little bit of the paint that makes the painting or whatever, but we'll just do 1 over distance times distance, all that times the direction, because it's a normalized direction, so that won't add any actual force, just the direction, and then multiply that times the attractor force. So this first term, what it's doing is basically makes it so that the farther away the particle is from the attractor, the less force it's going to be acting on it. So it's sort of like a gravity, you know, like the further you are away from something, the less force it's going to be. In terms of how this works in the universe, it's probably a little more complicated than that, but this works for most, most of what we need. And then instead of just setting the velocity directly, we're going to do velocity plus equals force. So that force is going to get applied each time, each frame, basically. All right. Does everybody have that? Okay, that's cool. So the new ones that you need is the transform, attractor transform, and float attractor force. That's cool. I'm going to make this a little wider. It's a little easier to read. Anybody tried it? Did it work?
The attractive force in it.
Yeah. So if you're ready to move along, yeah, just make a new game object. You can drop that into the attractor transform and set the force and move it around. I'll show you once we're sort of ready to go. So if you make the force negative, it should attract it. So add the force to the velocity and then add the velocity over delta times to the position. You guys getting it to work? Been moving around? Not doing anything?
It's moving, but only like left and right. It's never going up and down.
Interesting. Let's see. Okay. Is that working for you? Did I calculate these directions wrong?
Yeah, mine is sort of repelling in two different directions.
Okay, cool. Let me take it. You just need, it's going to be a compile error. Wait, Sears is not doing this. If your kernel index out of range error, it means that there's a compile error in the compute shader. So it will tell you if you go into your shader and edit it and save it and then go back to the editor, it'll compile and throw errors and should give you a little more information. Yeah. So yours doesn't. This is what mine is looking like.
Would you be able to pull up the compute shader?
Yep.
Sorry, that looks like a lot of fun. I don't want to mess with it. That actually looks like great compute.
Trust me, I've done this a lot.
It seemed like it. Attractor position is a float 3.
Correct. Yeah.
Oh, it's because I can't spell. That's all it was.
I always copy paste variable names for that reason.
I'm coddled by Visual Studio.
Yeah.
It doesn't do autocorrect.
Yeah. Shader programming is very humbling.
I would really download a plugin if this was going to be something that I was considering a lot.
Yeah, maybe I should consider that.
What's that?
Maybe I should consider that. It's like using the GUI.
Yeah.
That's what I know.
That's fair.
Oh, I guess it's based on some notation options. It's not exactly tracking.
In C Sharp, nobody defines attractor forks. Did I miss a line?
What's that?
I have private code attractor forks at the top.
It should be public so that you can change it in the editor.
That's fine. Oh no, that's not.
Maybe that's why I have no forks.
Oh yeah.
Do we define it in the script, or is it just like?
That's just something I edit in the editor. You know, you can control it from anywhere.
Oh, well,
Again, I like to make those ranges.
Like it wasn't moving, it's like it's probably didn't give him. Oh, that was fast. Give that more.
Cool. Does anybody need to look?
No, not good. Yeah, it's force negative, minus. Force minus half percent. Or minus. Just double check. It's moving. You gave it a pretty good
Yeah.
What interference if I try to change settings, custom number, whatever?
What's that?
It's just frozen. Yeah. When I try to change the number parameters, it just frozen.
No, we just use delta time. We use delta time to figure out how to do it.
Are you the person? No, I think I need a recommendation on that answer.
I say you just try this.
Shouldn't like change number parameters.
Well, once they pass away from the initial, once they get flustered for it.
That's the biggest thing is update on the first. I say you just run with it and act like you've been doing this the whole time. Like you should be like, I intend on doing this.
Yeah, does it look cool?
Yeah, it looks so cool. Not anything like what you made, but it sure looks cool.
Yeah, it's just really sensitive to it.
I think she doesn't know why. That's the catch.
Probably, I mean, the real reason for that is to be like a power.
It's doing the same thing. You think it's the GPU?
For me, what was happening is I got, figure out, the force.
Do you have it edited? But I would imagine it would just outright not work. It would say it's like,
I tried to set up my scene where it was like, optic side,
I would suggest like, always like to, try to simplify things really, like what you expect it to do, and then
Or like this would be the best part. Like this is over like
all right, I'm gonna go ahead and push what I have now too.
you made CPU enough. Alright, so like I think this is like I think you might actually is that acceptable? That's definitely
Oh, mine is cut off.
this one doesn't correct you as much as the,
Yeah, seriously, it's on another case.
and then you have like one of those textures around to make it cool. Yeah.
Okay, I pushed the latest to GitHub of what we just did. If anyone needs to pull, for our friends on the integrated Macs, I'm not quite sure what to tell you. That might be something I have to research and get back to you on. And maybe we'll try to fix it together and fix the repo. It'd be nice. So cool. As you all noticed, this like gets pretty intense pretty quick. So we're gonna go ahead and add a damping force because that's like just something that is really useful. You can sort of like it's like when you're going through a viscous fluid like honey. Like when you're going through something that's thick, there's an opposite and not equal force pushing against you always. So we're just going to add something going against the velocity to simulate like moving through a fluid. So we'll call that a damping force. And we'll make that a range from 0 to 1. And then we'll go ahead and set that in our shader. Simple. We'll set it damping force and damping force. Then we'll go ahead and add that to our shader. And the force is going to be the opposite of our velocity times our damping force. Cool. So that's basically like just going to give us a way to control that speed, because as you guys saw, it gets out of control a little quick. People need to see that code still? Yeah. Cool. All right. Cool. We'll see if that smooths that out a bit. Add like a little bit of damping. Yeah, that's much nicer. So now if we move this around, we can start to kind of like, the particles get a lot more damped, so they're not going to go crazy and fly off into space. And just sort of play with that, find like a good value. One thing I forgot to mention before is that the other reason these are all going crazy is because at a certain point, this value, distance, is going to get very, very small as it approaches as a particle approaches the attractor force. So as that approaches zero, the force is going to basically approach infinity. So that's something that we need to limit here. So we can basically do that by doing dist is equal to the maximum value of dist and give it a value maybe like 0.2. That'll limit how massively that force is going to explode. So in addition to the damping force, is that not enough? What do a little bigger. This thing is kind of strong. There we go. So you can play with those kind of values. It's sort of like a maximum force that you would apply on it, you know. to find something. Like I said, once this is sort of like the template, and like everything that goes in here is like really just like the ingredients to make it look how you want to look it. It's like it's all that work to get to like a creative part, but but once you sort of have it, it can be a lot of fun. And then so maybe we'll just stick with like kind of a bigger value there, so it doesn't get too crazy. That's pretty nice, like 1 in there. So to get that, you just do dist equals max of this one. So what that's doing is it's just making sure that value does not drop below 1.
Do you get more control like yourself versus using their built-in system? Because I've actually never used it before.
I have not used it a ton either since I've been writing these kind of systems for a couple of years. I would say that yes, you get more control, of course. You can do quite a lot with the built-in systems, especially now they've added like vector fields and noise fields and force fields and all this stuff, which is all stuff that before VFX Graph I had built myself. But you know, for me, it's like I'm driven by like the understanding, and like it's fun to like create new features that aren't in Unity, because then you know you can do something that not a lot of people can. Hey, look, it's Cosmic Sugar. Yeah, so even there, like just a really simple, this is, you know, a single attractor, not that many particles, you get a pretty nice, fun little thing to play with. Interactive, this will work in VR.
With the velocity.
Yeah, I should probably do some stuff like that. I think this is good for forces for now, because it's already getting kind of late. So, as David was saying, it's really awesome too now that we have like these kind of this kind of stuff built. You can use all that data that we're generating in the compute shader to kind of color the to change how they're rendered as well. So if we want to open back up the render shader, and try to do some fun things here. So we're just going to calculate the color in the vertex shader. So we need to add a float for color in V to F. And we'll just use the color channel like we were doing before. And that's in V to F, so we'll just do like O dot color for now. We're going to just make sure this is all hooked up right. We'll just do float for 1, 1, 0. And then in the fragment shader, we're just going to set the color to I dot color. Cool. And so that now should change the color. Cool. They're yellow. Great. Yep. So a little too quick. So this is the same thing we were doing before, where we're adding in the render shader a color in the V to F structure. And then we need to set that in our vertex shader. So right now I'm just setting it to a yellow constant color here. And then it's just getting set in the fragment shader, the I dot color input. So cool stuff that we can do here. We can define 2 colors. So maybe we'll do red and that yellow. And we're going to do a linear interpolation based on the speed. So we'll use that smooth step function that we had before. And we'll just try this. Smooth step from 0 to, I don't know, maybe 5. And we need the length of the p dot velocity. So we're, thank you. Let's make it, I don't like that color anyways, yeah. Yellow to purple or something. Whatever that is, so. Huh? Perfect. It's like the non-existent colors. So that smooth step is going to do basically like smooth out the velocity and make it return a value between 0 and 1. And then that's going to define the interpolation between these colors. So if everything worked out right, I'm missing a semicolon, or I'm missing a parentheses most likely. Now based on the speed, we're getting those colors changing. So you can see where it's really close and it's going faster. It's a yellowish color, or it's a bluish color, cyan. And when it's slowing down a bit, it's more of a yellow. So it's one way that you can make some nice colors that sort of respond to the properties of the system. I might just, start sort of demoing and showing some stuff at this point, if and I can push this all later. So another very useful thing we talked about earlier was noise functions. Those work incredibly well with particle systems. So if we want to include, I have a noise function in, I believe it's shared noise.hlsl. Yep. And let's take a look at that real quick. Oh, maybe that is not the name of the function. Sorry, noise.cg include, CGINC. So I'm going to want to do 3D noise here, which means we basically have to do three different noise functions. Have this all, and I'm going to look at my cheat sheet. So I have another function. If you open this particle motion.compute, there's a noise3 function. But that needs a lot of other parameters as well. Well, we can just write this. So we don't need these frequencies. But basically, like noise3, you have to do 3 noise, called S noise 3 times, and you need to basically offset those because that provides a seed for the value. Otherwise, they're all X, Y, Z is all going to be the same value. We don't really need this. Just to modulate the noise. These offsets don't really matter what they are. You want to get them so that they are out of phase with the noise, but you basically just have to do that by look and feel. And I don't know if you guys, anyone's typing this out or if we should just go through it. So now at this point we can add a force plus equals noise of, we're going to do it based on the position. So that's the position in world space, so it sort of makes it act like it's in this vector field. Let's see how we did. Hey, it actually just works, cool. So, yeah, so you can see sort of where it's popping out, and we'll slow this down a little. More of that, yeah. So this is something that becomes very recognizable, this like noise function. But you can see now it's adding the noise into the system, and then it's also being attracted to the attractor. So this is how you sort of like can combine multiple things together, start creating like a dynamic system. What's that? Looks like space.
Well, like you're casting a spell or RPG or something.
Yeah, exactly. I mean, yeah, it's totally like the uses for all this stuff, you know, it's like, oh man, just killed it. Starts to get a little bigger, you know. It's my attractor. Oh, there we go. Yeah. Seems like it's not attracting anymore. Which is interesting. There might be too much noise on it. Yeah, I mean, like I said, there we go.
There's another kind of noise you can look up. You guys have heard before called curl noise, which basically helps prevent like all of this noise that's sort of bunching up. And curl noise basically maintains the volume of the particle. So you get all the turbulence but without the bunching up.
Yeah, I used the cheap noise function.
Yeah, curl noise is 3 times more expensive than regular noise.
Because it essentially, I think it's like same as gradient noise, right? It's basically like calculates the gradient around the point, I think. If you guys want to see I can just push all this code, but also I can show this again. Is that easier if I just push it right now? All right, cool.
Well, I want to see the clean version rather than my sloppy version.
Wouldn't it be cool if the little cubes that were orienting in the direction of the wall thing?
What was that in the back? This is gonna turn into a special request show, I think, at this point. It's like, just shout out what you want to see and we'll just do it. Like, honestly, I mean, seriously, because like, at this point, it's like, sky's the limit. Like, whatever way you can think to like move this stuff around, like get data in there. It's like, maybe it's like a sensor out from your phone where you're sending, you know, tilts. Like, all that stuff is very possible. Like, this is all you need to like hook all that junk in.
And none of this stuff is like managed by the engine, right? It's just rendering. You're just drawing it.
Yeah, basically.
Like,
But
it's not like there's 200,000 moving objects. It's literally just like mentions.
right, it's instanced. So geometry instancing is something that's supported by GPUs.
Sure.
Yeah, and I will show you now what I've sort of been going down this road of doing more like mesh-based particle systems. So let's see. I think if I use this material, this should work. Let's see. Oh wow. Yeah, so this is like, for example, same deal, like not really game objects, but it still actually like goes into the Unity lighting pipeline, which is something that I had a really hacky way to do this for the last couple of years, and the graphics, that's the other reason I use this graphics API, is because it goes into that system, and it's really awesome. So this system also works with like drawing a ton of meshes, so you can play with that. I don't know why the color is kind of not great, but it's kind of boring. Something that David was just talking about, alluding to, that is, so instead of angling to the, instead of angling like as a billboard, you can angle with velocity of a particle. So if you're using like meshes and stuff, you can have stuff sort of facing the direction it's going. Maybe this is what I need.
Like an arrow or something.
What's that?
Like an arrow.
Yeah. These kind of look like fishes, maybe, or something. So these are all like
Flocking. Yeah.
it's sort of like fake flocking a little bit. Yeah, it's not real because they're not like responding to each other. Yeah, so.
Some Donnie Darko. That one's
Yeah, right. It's a little like Donnie Darko, and if you do some cool like screen space rendering, it could look a lot like that. Let's see. Let's go that way. Oh man, haven't even gotten there yet.
One more thing about that kind of geometry is you don't have the overdraw issues with the transparent blocks. So there's going to be more geometry which will affect performance, but then there goes overdraw which will affect performance. So all this stuff is like a balancing thing.
So one obvious issue with something like this is that at a certain point, everything might kind of like go off the screen or sort of like not really be where you want it to be, right? So something that's really common for like special effects particles is you need to add an age and a lifetime for your particles. So let's go ahead and add that together to this compute shader, and need to update also all the structs. So it's a good thing to show you guys. So say like I've built my basic particle system, but I just like want to add some other feature, right? So I need to store some other data. So as I was mentioning, all those structs have to line up. I think let's actually go into the add features scene together, if that's cool. Make sure everyone's kind of, this is the wrong one, but the add features one. I guess this doesn't have noise, it's the only thing. So what I've also done here is I've broken out the force into a separate script where it's controllable as a separate object. And you can also, I don't think the range actually does anything. But what I wanted to show you here, this might be too complicated to get into right now. Split the two things.
Will you talk about the concept and just like breeze over stuff?
Yeah. So generally, when I build a system like this, I split it up into the solver and renderer components that are separate. This is all in that add features section. So I'll just show you kind of how I tend to build stuff. I have the particle data, that struct that we would have seen before, define thread groups, and this is where all the buffers get created, and then initialize the positions, and kind of like what we had already built before. I realized that maybe we should just keep going with what we already have. I think let's do that. Okay, so apologies. I'm going to go back to the build a basic system because we're doing pretty well there, I think. Cool. So that's all great. It explodes out. It's fine, but I really want those to like continually like get reborn, right? Because that's typically what you might want to do if you have like a flame effect or something like that. Like you have like your magic wand or whatever. You want it to like continually emit. So I need to add some data here to track. So if you guys want to follow along still, if whoever's got energy left, we'll go into the particle system basic, and we're going to edit that data structure that we built before. So we're just going to add a public float age, just to keep track of the age. Here we need to increase the stride by 1 float, so because we just added a float. And we're also going to add a float for the life, because we want them to not all have the same life. So then the stride total will be size 8 times size of float. I'm curious if this is going to help if this will work on yours now. So we also want to open the 2 shaders that are referencing this type, the compute shader and the render shader. And where we define these structs in here, we'll add the float age and float life. Definitely would recommend breaking these out into a separate file that both the shaders can reference. That way you only have to edit it in one place. That's what I typically do. Cool. So now we have an age and a life for each one. We initialize, and let's just go ahead and in our initialized particles, we'll set our age to 0, and we'll set our life to some random range. I'll say between 1 and 4. It's usually pretty good. It's probably something that you'll want to be able to have scriptable and changeable. In fact, let's go ahead and do that right now. So we'll add a vector 2 for age or life min max. It's equal to new vector 2. We'll just have that default to 1 and 4. So that means basically what it's going to look like is that it'll be some random number between 1 second and 4 seconds that each of these is going to live. So instead of doing that, we will do random range between life min max dot x and life min max dot y. Cool. And then in our particle shader, basically we're going to need to do something with that when that thing dies. So, sorry, in the update particles compute shader. So I think all we're going to do here is in the update. If p dot age is greater than p dot life, we're going to set p dot position equals to 0, so it's going to set it right back to the origin. P dot velocity equals 0. P dot life, p dot age, excuse me, is equal to 0 as well. So that's basically going to reset everything, and we'll just return from that one. One place where I use if statements is probably a better way to do it. And down here, we're just going to increase the age. P dot age plus equals delta time. Did not seem to work. So, what's that? Yeah, so let's see why that is. Age is greater than, because I did not write the buffer back. So if I need to write that back after we set up the age setting back to 0, or else it's just going to continually go through that. There's that, and now we sort of have like, this is kind of not a great way to emit, but we have this little like emission of stuff from 0, 0, 0. And these are still cubes apparently, which is why they kind of look funny like that. They got like this weird little like
What if you wanted,
fire hose.
What if you wanted the effect to end once all the particles that you instantiated died? So it seems like you'd be in the compute, and you'd need to like go back and tell Unity to like delete stuff out of the list. Like, how would you do something like that?
So, like I said, none of this is known about on the CPU.
Right.
I think you'd need to qualify that problem a little bit better to find the solution.
Okay.
Like, if you know how long an animation, for example, is going to last, then you would just kill the whole thing, right? You'd keep track of that on the CPU side.
Okay.
You wouldn't ever want to like try to pass data back from the GPU to say like this is done. I can't really think of a circumstance where that would.
Let's say you have like a stream of water.
Yeah.
And the water just ends. You wouldn't want the whole batch of water to just disappear all at once, right? You would want like the stuff at the end to disappear, and then this stuff stops coming out.
Yeah, so that's like a little bit more like a burst spawn or some kind of thing. I mean, it's all very doable. For that, you basically would have to stop it from spawning. Yeah, so I mean, you do stuff like that, David. I don't know how you approach that problem. With you shoot out points in Cosmic Sugar.
I don't shoot out any points in Cosmic Sugar. That list exists at the beginning, and they never have.
Oh, I thought you could draw. Not anymore.
Positional points.
Okay, yeah. So that's one approach, is you have like a static, you have all these static, and basically like, if you can just like reposition them to where you're emitting.
You said it's expensive to send a message from the GPU, but even just the one-time message at the end, is that really that bad?
It's not that bad, but you got to figure out how you define that message also, like where the logic lies. Because there's no like collisions. So you could define them somewhat, but I think you'd have to really think through that problem and like figure out why you were trying to do that. And most likely, if you're trying to send data back, there's a better way to do it, or there's like some other way to do it. I try to definitely keep mostly like view logic and like visual effect stuff on the GPU. Like anything that's game logic, you just don't want to try to do it on the GPU. It should be the visual representation of the stuff that's happening in your game. So that's looking pretty cool. Got like noise we're emitting. got it coloring by the speed.
So what's a good way to fix the fact that you emit, or else like it will like keep like elevating like points?
Yeah, this is not a very good way, obviously, to emit. Like, that doesn't look very good, right? So,
Emit, can you like offset it by like the initial position?
you could do that, but you'd have to store the initial position in the velocity. What I prefer is I prefer to do everything procedurally. In fact, if you look in one of the other examples I provide, I don't use the CPU to initialize particles at all. They're all initialized on the GPU. So I'm going to pull some of that code. Let's see. I really like sphere picking, like finding points on a sphere. So I've got a few utilities that I've written for this. So I'm just going to go ahead and pull this. Actually, really, I just need random inside sphere ID. And that is defined where? Right here. Cool. Got a reference for this one. So that function is in, sorry, this complete, the particle motion.compute, which is the complete system. And this is basically like a way to very quickly, using an ID, basically calculate a pseudo-random point inside a sphere. Basically like exactly what we were doing on the CPU, but this is how you do it on the GPU. I need to include random, which is also included in this shared folder. And this is an example of random number generators for shaders. Random is a very difficult thing to do, so there's like a few different algorithms. This one's pretty decent. You can pretty much just find these online, and that's on there. So you pretty much just have to search for those kind of like little things, and that's how you like link all this stuff together and try to maybe improve it or find ones that are improved. There's a lot of really bad random functions that don't look random at all. Again, sometimes you're better off like baking a texture with random data and then using that. So I'm going to include this and then do random inside sphere. And then I'm going to multiply that by a sphere size. I'll need to go back to the particle system. I'm going to make a sphere size in here. Oops, range from 0.1 to 4, something like that. Float. So this will be the size of my emission. Go ahead and set that float as well. Sphere size. Cool. So now instead of setting the position down to 0, should be able to emit out of the sphere. And what did I do? All right. Wow. Okay. So now you can kind of like control where it's emitting from. This noise is getting a little obnoxious, so I'm going to cut that down a little bit. Reduce the frequency of it. So it's make it a little bit nicer. Maybe make these particles a little bit smaller. Yeah, so now these are just sort of like, I think is it going to that attractor, or is it even going? Yeah, there we go. Great question. Thank you, David. Yeah, so there's like your little emission. Yeah, doesn't right now respond to the transform. I'll go ahead and add that, format it, because that's a nice thing. Emission point, just in case you want to be able to move it around. Set vector, emission point. That'll just be the world transform. That way we can go ahead and add that to the start here. That way we can move around the particle system, and it'll actually like emit from there. Something that you'll probably want to do. There we go. Yeah. Cool. So I do have a nice little feature thing for this, for some coloring. One thing I really like to do is basically like be able to, and something you'll see in VFX Graph a lot is like color over lifetime, or doing parameters over lifetime. So this is some little gradient thing that I built, and I'll show you how it works. And this is in the project, so feel free to use it. You can define like a color over lifetime gradient. I'll just go ahead and put that in our editor. And basically this is just, this will just like allow you to use the regular gradient editor that's in Unity, but it bakes it into a texture, and then you can use that in your shaders. So it's really useful. You can use it to parameterize almost anything. I use it to color stuff, but you can use it for all sorts of stuff. The only thing that's a little weird is that you have to bake it, so we'll just do color over lifetime dot bake texture on start, and then when we're setting up the material, we'll do that dot set texture, call that color over life text, color over lifetime dot texture.
One-dimensional texture?
It is a one-dimensional texture. So I thought you could define the size, but I guess not. It's not public. Yeah, I think it's like 512 or 1024. Generally don't need too much resolution on these things. But basically, so what we're going to do is, this is a one-dimensional texture that creates this gradient, and basically like as the particle approaches the end of its life, it'll pick a color on this gradient. So we'll go.
So like we're colliding the gradient over time?
Exactly, yeah. So have to do is define a texture 2D. Sampler 2D? Sampler 2D. Yeah. Color over life text. And where we're calculating the color, instead of doing it based on velocity, we'll do something like life percent is equal to smooth step from 0 to p dot life, p dot age. So basically that's just going to create this smooth value between 0 and 1 based on the age from 0 to the life. So then we're going to do O dot color equals text 2D, LOD, I need to find that. Text 2D, LOD of the color over life text. And we're going to use that life percent 0.5, which is just sort of in the middle of Y. It doesn't matter, it's one-dimensional texture. And that is the level of detail which you have to do when you're sampling a texture in the vertex shader. I spelled that wrong. I also did that wrong. There it is. Damn hell. Now over the lifetime, we should see it change colors. It's not very easy to see, but there we go. It's kind of nice stuff. You can, you would be able to change this live, except that.
You bake it once, right?
Yep, but a trick that I do for that is I use the onValidate method, and I can bake it in that. OnValidate basically is anytime you change something in the inspector window, it'll call that. So it's great for doing stuff live. And it's just a render texture, so it'll update and no issues. So yeah, if I'm like designing something, I definitely need that, and then I can, you know, figure out what colors are going to look right. It's nice to be able to just like swap them out super easy. Maybe if maybe instead of like, you know, the lifetime, I decide that you know, actually it makes more sense to like have that be based on the velocity or something like that. So go back to your shader. Instead of doing the life percent, we can use this like you know, velocity function that I already made. So speed lerp, something like that. So instead of doing the life, maybe I'll do it based on the speed. And, you know, redefine the look of the system just by basically changing how it's colored, you know. So those are the kind of things that you really want to like think about when you're designing this stuff. It's like all this data is available to you. Like, how do you turn that into something that's cool to look at? Like that's really kind of what it comes down to. Is everybody like totally dead? Yeah. Okay. Cool. Me too.
It'd be worth going up over just like quickly at a high level, like what like next steps are, like emitting from a surface and emitting from a skin surface, and then reforming, like turning faces of an object into a particle system. And
The sky's the limit.
some stuff.
Emitting from the skin mesh or something.
What's that?
Yeah.
Like emitting from a skin mesh.
Yep. So
So-
yeah, they spent a long time doing a bunch of projects where it's like 3D avatars get turned into particles. So that's like
have a demo of that.
Oh, you do? Is it here?
Yeah, I can show it. This is a, if everyone just wants to see stuff, that's cool.
This is like collisions between particles?
Yeah,
Is this in the project somewhere?
no, sorry. This'll like load.
Yeah, if you're gonna do collisions between particles, you can't have millions of particles.
10,000, 50,000, 100,000?
Depends on like what your mesh is. So this is, wow, this is an example of a project I did recently that uses skin mesh, particle systems, particle collisions. For that, you need to, for collisions, you have to keep track of those collisions inside of a 3D cube. Meaning like instead of texture, you have like a stack of textures, and you keep track of each point in there, like whether there's a ball in there or not, and then based on if there's a ball in there, you have to basically like know that there's going to be a collision. What's that? Yeah, this was actually a retail installation for a particularly large shoe company, but I won't mention.
Until the logo flies in.
Yeah, right. No, I took the logo out. So this is something that I built, and this is all in compute shaders, and I think this is maximized, so I don't think I can, let's see, I can get it out of it. This is, for example, like 91,000 particles, and it's all these spheres. I made some like kind of like low impact spheres, but then yeah, basically the grid resolution refers to like how they can all bounce off each other. I'll just show you real quick because I don't know why not.
So you're running your own physics detection and correction with
Yeah, correct.
the compute shader?
Yeah,
So you basically build physics from scratch?
yeah.
Okay.
Because there's no way you could ever do this on a CPU in
Sure.
Unity.
No, I was going to say this
So,
would be frozen.
see if it works.
because-
So there's like the skin mesh where all the attracting to the body.
That's so
It works with two people. You can come up here.
That's awesome.
I don't know why my leg is kind of up there, like doing the stanky leg thing.
Table's hiding.
Yeah, I think so. Should work. Maybe. No. I don't know. I didn't write the Connect code. There you go. There's your body. Yeah.
It only likes me when
I
it
don't
does.
get too close. Yeah. So that's like, this is like an example of stuff. I've been doing a lot of stuff with particle systems and bodies. Our inverse kinematics is very strange. But yeah, all this is a single system, so it's basically like it attracts those as it, it selects a bunch out of those and then attracts it to the person when they're detected, and when they're not detected, it basically goes back to this idle state.
That's very cool.
But thank you.
I'm seriously amazed that it runs, there's so much physics stuff happening.
Yeah. So I can send you the paper that I followed if you guys are interested in this kind of stuff. It's like in the NVIDIA GPU Gems, which is like a really good resource as well. You can see like all my links that are opened up. So like this is like all these textbooks that have all sorts of crazy like GPU techniques that are from like game developers, from like SIGGRAPH. I haven't even read this, but I want to, it's like such a big rabbit hole, which is great. There's a lot to explore. Yeah, and as an example, I'll just show you a couple things more, and then we'll chill out. But asking about debugging and stuff like that, like this was really, really difficult to debug. Because I built it basically for this project, and so I had never really worked with this stuff before. So why is my screen tiny? So basically I'd made like all these different things where I could like all this like visualize mass, visualize force, all of that refers to data that's like being passed through the compute shader and being calculated in the compute shader. But in order to basically like debug this, I had to like know what was happening. So like this is, it's really hard, it's kind of hard to see, I guess, but like this is basically the forces that are acting on an individual particle at any time. So like I said, I'm just, oh geez, you like just know to, if it's red, it's going positive X. If it's green, it's going positive Y. And like, you just sort of like start to build up a way of looking. All this stuff is like getting pushed negative right now, so that's why it's all black. The one that's pretty cool to see is like, yeah, you can see when those explosions happen, they get a little bit, it's not the right material. Something in here is like the collisions. So every time a ball hits each other, I color it blue. So you can see when there's like a collision happening. That was really helpful. You know, this system started out as like basically just drawing a cube of balls and like dropping them, you know, and then basically just once you know you get that working, you make it a little more complex and a little more complex. Let's see. This is when I was debugging because I was trying to, so I was talking earlier about how I can use a texture to like affect stuff in screen space. So what I'm doing here is I have these like two, let's see, I'm like generating the noise in a separate compute shader. And you can see that here. So this is like this noise texture that I'm generating in a separate compute shader. That gets fed into this particle system. And then basically using the screen UV, I sample that noise and get it here. And then like apply that noise as a force. So the noise is being calculated separately in a texture and then use that to affect this was running on I think it was on a 2080. It was whatever. I told him to get the best thing possible.
It's like one installation, right?
Yeah, exactly. Yeah. Yeah, same. Here's for the explosion. It's just like it's just a point that draws vectors out from it to make like an explosion. You know, so it's a lot of like trying to determine what your problem is that you're trying to solve, and then make something to solve it. You know, it's like once you know what you're trying to solve, it becomes a lot easier. It's usually figuring out like what you have to solve is the hard part, in my mind. So yeah, with that, I think everyone's probably pretty beat. But if there's any like questions or want to talk about stuff. What's that? Yeah, I probably. What's the question? Who made it? Or how?
Yeah, what was your approach?
I didn't do sound on this. It was somebody else.
What was the approach to this case? Was
Okay.
actually
Yeah, so because this is something that's relevant to you, right? So, for example, I don't know if we ever actually did it, but we had talked about like those explosions should correspond to sounds, right? So how that would work is basically like when you fire off an event that triggers a sound, I would receive that event and basically create that explosion.
And then you have just background both.
Yeah, I think so, yeah.
So it's not like audio reactive, not fully audio reactive.
No, this is not audio reactive. I would have loved to do that, but it was, you know, it's a faster project and like not, wasn't like a strong, you know, tight collaboration. This was actually installed in Australia, so I've never gotten to see it. Yeah.
This is super random, but how do you do like smoke, for example? Is this like the same kind of path? You're just using like a different texture?
Yeah, so typically what you would do is what's called a flipbook animation for smoke. So that's where you basically, let's see, you can get these textures that are basically like like a sprite sheet, right? Exactly. So they look kind of like this. You would normally, you know, you can get them online. Normally you would probably simulate it in Houdini if you want to like do something really nice.
This isn't a particle, right? This is just literally a spray.
So it's what you do is you have a particle system that emits sort of like in that noisy way, like with the noise, and then you flip through these sort of like as it grows on. You can do all this with VFX Graph. You can like basically, so it goes from, you know, that point, and then it basically just like fades out. Maybe you'll change the size. Actually, yeah, making a smoke thing is like one of the first kind of like VFX tutorials that you'll find a lot of places. I don't know, anything else to add on that? And you can work that into like this kind of system. It's just you have to write it all from scratch. I've also made some really funky smoke with like world space noise, like layering a ton of noise together, but it was not very performant. So I tried to use it in a VR project, so, but they kind of nixed it.
Displaying data that already exists,
Like point cloud data?
data like you can like display MRI as part of the system. So just
Right, yeah. Well, I don't know if this project's online, but did I spell that wrong? I don't know. Yeah, I've done like some LiDAR scanning type projects, and this is an example of one where basically I was asked to help with the rendering of this LiDAR scan. So it's a LiDAR scan in a cave, and basically like wanted to create this sort of like more dynamic system. So this is data that was taken from a laser scan and then brought it into Unity, and yeah, so it kind of looks like this. And basically what I did with that data is it didn't have any color information or anything, so I like applied these gradients. I applied a little bit of movement, so like you're inside these tunnels and they're kind of like moving a little bit. And I think I made some stuff where like if you get really close to the points, they disappear so that you don't feel like they're right in your face. So that's a lot of the kind of stuff that I've done with this in like professional projects or, you know, film projects, that sort of stuff. This was a VR project that just got released recently.
anybody have ideas for projects that they would want to do and maybe need some tips about how to approach it?
I would fold the entire world like Inception.
I think you'd need to, there's some people that are doing like 4-dimensional type games. I'd look in that direction.
So are you talking about like take a world and like fold up? So that would all be done, that would be a particle thing, that wouldn't be a compute shader thing, that would all just be
Matrix.